Hello, everyone. Welcome to the March 2023 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. And it's hard to believe it's March 2023. I know that's an eternal kind of thing. Time keeps passing. We got our first snowfall of the year here in Baltimore just the other day. Not much of a snowfall. Technically, snow was falling from the sky, but it was only for a short period of time. Not that much. Instantly evaporated. But it struck home the fact that it was our first, and it's almost March when I'm recording this. And that's very, very rare. You know, Baltimore is not a frigid northeast climate, technically south of the Mason-Dixon line, even though just a bit. But usually, as I know from living in Philadelphia for a long time, which is not that far away, you will get snow in the winter, sometimes quite a lot. And this year, and apparently in recent years, there's just been essentially zero snow. Also, when I arrived here last summer, July and August were brutally hot and quite humid at the same time. Now, you may have heard the world is getting warmer. The climate is heating up. The fact that we've had a very warm winter and a very hot summer doesn't by itself imply that climate change is happening, but it's compatible with that. And the reason why I'm mentioning it is not because I advocate people thinking about the reality of climate change based on their local weather conditions, but because it does drive home how that visceral impact really does matter. You know, we're moving into the phase of global climate change where people are going to start to notice. It's going to be harder and harder for people to stick their heads in the sand and pretend that nothing is happening. In some sense, if we completely stabilize the climate immediately right now at the present value of all the different parameters, we'd be fine. It wouldn't be a huge difference from what things had before. The real problem is that it's going to continue to deviate from what it usually had been. So it's important that people catch on that this is a real thing. And I don't like the fact that the summers are really going to be very warm around here. On average, some of them might not be, right? There are fluctuations around whatever mean is happening. The winter being warm is kind of nice, although it'd be nice to see snow sometimes. Anyway, it all just feeds into this question of what kinds of things make people change their minds, update their credences on various things. Of course, people who've been following science and don't have some hidden political agenda or explicit political agenda already know the climate change is happening. But to feel it in your bones can be effective, be powerful for people who are not already there. So I'm interested to see what will happen going forward as people notice that things are not like they used to be. Anyway, that's not a very profound thought, but it's all I have to begin. I want to get right into the AMA. It's a long one as usual. I feel bad that I had to not answer a lot of good questions. Reminder that these questions are asked by people who support Mindscape on Patreon. You can be one of those people. Wouldn't that be awesome? Go to patreon.com/Sean M. Carroll. Sign up for $1 per episode or however much you want to pay. And you get to ask these questions as well as getting access to ad-free versions of the Mindscape podcast. There's also a podcast webpage if you want transcripts. We have transcripts of every episode. You can search the transcripts if you like. Oh, and here's something very fun. In the AMA today, someone pointed out that they would like an index of all the questions that have been asked, because I mentioned that sometimes the reason why I will not answer a certain question is not because it's a good question, but because I feel like I've already answered it several times. So Siddhartha has gone in and made a question and answer record of all the AMA questions into a table format that's available on Google Docs. I will put a link to that in these show notes because I was mentioning that we have show notes, transcripts, etc. That's on the podcast homepage, preposterousuniverse.com/podcast, available to everyone, not just to Patreon supporters. So you can find all that, and soon you'll be able to search the AMAs. Of course, you can only search the exact words. It's not a super smart algorithm or anything like that, but maybe that will help people find out whether or not their question had been asked. So with that, let's go. first question this month is from Scott, who says, do you have any comments on the recent astrophysics news that supermassive black holes might be the source of and coupled to accelerating cosmological expansion? And what does it even mean to say these supermassive black holes have dark energy inside their event horizons? This actually, it was not just Scott who asked this question. Several people asked this question. Sorry, other people, for not mentioning your names, but I thought I could just condense it into this one thing. I don't have anything especially brilliant to say about this, but I wanted to explain why I don't have anything especially brilliant to say about this. So what Scott is referring to is there was a paper that just came out by Duncan Farrar and collaborators, and I think there were two papers, and these are, respectable people. These are not crazies off the street. And it got a lot of attention in the media and elsewhere. And the claim is that black holes can grow faster than you think. We know that there are black holes out there in the universe. We know that galaxies tend to have supermassive black holes at the center of them. We think, by the measurements of the actual black holes, that even though they're supermassive, millions or billions times the mass of the sun, they're still very, very subdominant compared to the amount of matter and energy in stars and gas and dust, not to mention dark matter and dark energy. The usual standard picture is 5% of the universe is by mass, or by energy, I should say, is ordinary matter, the particles and atoms and things like that we've already know their types because we've discovered them here in the laboratory. About 25% is dark matter, which is some other kind of matter, some kind of particle or something like that that has not yet been discovered in the laboratory and doesn't interact noticeably with light. Therefore, it is dark matter. And 70% is dark energy, which isn't matter at all. It's something that has a more or less constant energy density. Even as the universe expands, the amount of dark energy per cubic centimeter remains approximately constant. And that's really the trick. That is what it means to be dark energy, because the important thing that the dark energy does is that it makes the universe accelerate. It changes the way that the expansion rate of the universe evolves with time, so that it seems that the universe is going through an accelerated rate of expansion. This was discovered back in 1998, among other people, by my current colleague at Johns Hopkins and former Mindscape guest, Adam Rees. And this is the most important thing in the universe, as it were, for cosmologists these days. We don't understand exactly why the dark energy has the magnitude it does, etc. So it's a very respectable thing to try to understand dark energy better. And the claim is that black holes are the dark energy, effectively, that black holes grow, right? They accrete. There were not billion solar mass black holes at the birth of the universe. They came into existence and are growing. And the claim is that they grow so fast that even though the number of black holes in a region of space stays, let's imagine that it stays roughly constant. So you would think that as the volume goes up, the density of energy in the black holes goes down. But these people are saying, no. The black holes individually grow so fast that the total amount of energy density in black holes remains approximately constant as the universe expands. And therefore, the black holes are kind of like dark energy. And maybe they are the dark energy that is making the universe accelerate. And so the question is, do I have any comments on this? So my comments are, I haven't really read the papers very carefully. And the reason why is because they seem very unlikely to be on the right track to me. And I have to try to be super duper fair about this because I haven't read the papers. So how can I say that they're probably not on the right track? First and foremost, I could be wrong about this, right? Because I haven't read the papers, I haven't checked the calculations or anything like that. So I'm going on various feelings and priors that I have. And it's a completely fair question to ask, given how important it would be if this result were on the right track. Why doesn't someone who cares about cosmology and is a professional scientist spend the time to read the papers and check them? And that's the interesting question to talk about. And the answer is that, to me, from my perspective, when I read these papers, as someone who's done a lot of work on dark energy and general relativity, I wrote a textbook on general relativity, it seems completely at odds with all of my expectations and intuitions about how cosmology works, about how black holes work, about how we inventory what is in the universe. That's not to say that it's not right. I mean, maybe after all, my expectations are somehow wrong. But when I see a paper, even a published paper by, sensible authors that is flying fully in the face of all of my expectations, what I'm looking for is some acknowledgement that it flies completely in the face of all of my expectation, and immediately a reason why I shouldn't be skeptical, even though it flies in the face of all of my expectations. What expectations am I talking about? Well, black holes don't accrete that quickly in ordinary general relativity, in ordinary cosmology. Even when matter tries to fall into them, the matter heats up and often gets blown away rather than falling in. Dark matter has to literally hit the black hole exactly on to be absorbed rather than just orbiting it or something like that. So it's very much not what we would expect in conventional physics from black hole behavior. More importantly, like I said, we don't think that there is nearly as much mass and energy in black holes as in other stuff, just from looking at the black holes and counting them and adding up their mass and energy. For them to be the dark energy would mean that the total amount of energy density in black holes is much bigger than the total amount of energy in stars and gas and everything else that we see in the universe. That just seems wildly at odds with what we know about the universe. That's not to say that it can't be right. Like maybe it's right. Maybe the black holes are really tiny or something like that. But then black holes are not tied down to space-time. They can move around. If the black holes are tiny enough to evade detection directly, they should still behave like a gas of non-relativistic particles. In other words, like dark matter, not like dark energy. They should clump in galaxies and clusters. They should not be completely smoothly spread out like ordinary dark energy is, like all of the data say that dark energy is. Finally, this is saying that dark energy wasn't there. Well, let me put it this way. If the black holes are growing because they're accreting energy or mass from somewhere, from where? What happened to that energy? Is it just that there is some mass and energy that is being absorbed by the black holes, so the black holes are growing, but the energy and mass and other stuff is going down equally fast? Because if so, the total energy density is nothing like dark energy, so it would not be dark energy-like at all. Anyway, maybe all of these questions have perfectly good answers, but from my reading of the abstract, the title, the beginning of the paper, there seems to be no recognition that these are really big questions that you had better answer right away. As someone who myself has occasionally written papers that people initially are going to disagree with, I think, if I want other people to use their valuable time to pour through my paper and try to understand what it is saying and why it might be right or wrong, then I got to give them something. I got to give them some reason to do that. And to me, personally, these papers did not give me that reason. And you will notice that even though the papers got a lot of attention in the media and on Twitter and whatever, it's not from professional physicists and cosmologists that are pushing this. It's other sources that are making a big deal out of this. I have not heard any person who I know as a trusted, respected cosmologist who said, "Oh my goodness, yes, we've missed this. This is very important and probably the right answer." If someone does do that, then I would change my credences a little bit. But so far, I haven't seen anybody. So I'm very doubtful. I think that it will just probably go away. I would love to be wrong. It would be awesome if something like this were on the right track. I'm just personally a little skeptical. So I haven't done the work to be skeptical in a more informed way. Anonymous says, if we assume a past hypothesis, how can evidence inform our estimate of the age of the universe? If a moment of low entropy in the past is a brute fact, a fact worth about a Google bits of evidence, what makes the moment being 13.7 billion years ago a better brute fact than the moment being a trillion years ago or 10 minutes ago? Well, I think this is a really good question, actually, because it's kind of a subtle answer that I have a good degree of confidence in, but there's room for improvement, I think. What we do in science, in cosmology or any other science, despite some of the oversimplified versions you might be sold in high school physics courses or whatever, is a messy back and forth between constructing models of the universe and looking at data, looking at information, right? And the data that matters to us depends on the theories that we construct and the models and how we try to understand the world. And we judge models by various different criteria, including their simplicity and their naturalness in some sense, as well as, of course, fitting the data. There's absolutely things in addition to fitting the data that go into how we judge theories. So the idea of the past hypothesis is that there is a low entropy beginning to the observable regime of our universe. And so we identify that with the Big Bang, or very, very close to the Big Bang, about 13.7 billion years ago. And we don't know why. People like me try to explain why. I don't think it needs to be a brute fact that the early universe had low entropy. I think it can be explicable, but right now we don't agree on what that explanation is, so we take it as a fact. The question is, what other, could we replace that with a different brute fact? And the two options given here are 1 trillion years ago or 10 minutes ago, and both have their problems. A trillion years ago has the problem that we don't have any respectable way to evolve the universe from a trillion years ago up through the Big Bang to today. Again, people try, people build models, people write down theories, people publish papers, but we don't know how to evolve the universe through the Big Bang. So we keep that as an open question. What happened at the Big Bang, whether there was something before it? Maybe there was. I'm actually quite optimistic. I'm quite willing to believe that there was something before the Big Bang, but I don't know it, and I don't know what to do with it. We don't have respectable laws of physics that make that happen. So it is more legitimate to just say, okay, some conditions held near the Big Bang 13.7 billion years ago. As far as 10 minutes ago, again, that actually is completely plausible. Yes, you could imagine a brute fact that the universe came into existence 10 minutes ago, but you can't just say, and it had low entropy, right? You need, if you want to fit the data, to imagine that the universe came into existence 10 minutes ago looking like we think the universe looked 10 minutes ago, including all of your memories embedded in your brain, etc., as an enormously complex configuration of stuff. You cannot rule that out on the basis of data, but you can choose to not take it seriously if you have a better model, if you have a better theory. The idea the universe began in a hot, dense state, rapidly expanding 13.7 billion years ago with a very low entropy, that's a very simple model. You don't need to specify a whole bunch of individual people and their brain states or anything like that. And you can plausibly evolve from that to the universe we see today. So there's all sorts of things that are possible if you want to ask, could this theory of the universe be possible? But we're looking for the best theory of the universe. And the best theory we have right now is, for whatever reason, the universe 13.7 billion years ago was a hot, dense, low entropy, rapidly expanding state. Eric Fast says, "While I'm not a relativist about morality, I find relativism about meaning much more compelling. If someone chooses to dedicate their life to something I find uninteresting or even absurd, who am I to say they should do something else? On the other hand, compare a life spent doing something conventionally meaningful, raising a family, pursuing an ambitious career, making lasting contributions to arts or science, to a life spent doing nothing but watching reality TV. We would like to be able to say that one is more meaningful than the other and not just in a subjective sense. Do you think constructivism applies here? Can we construct a theory of meaning and then judge those who fail to meet our standards for a meaningful life? Or should we be relativists and accept that meaning in life is completely subjective? For me personally, I think this is, again, a very good question. I think it's a nice way of framing the issue. And I fall on the side of more or less being a relativist about meaning. I don't think that someone who sits in front of the TV all day watching reality TV is making a mistake in any objective sense, or even acting in such a way that I personally have the right to judge them. I can say that I personally would not want to do that, right? That's not my favorite lifestyle. I think that the reason why it's interesting to think about meaning in life, as we have done very recently here on the podcast, is not because we want to judge other people for getting it wrong, but because we want to do it for ourselves. Meaningfulness in this sense, if we're agreeing on what we mean when we talk about meaning in life, it's a more personal, individual choice. It doesn't affect other people in the same way. When we get to the question of whether or not sitting in front of your TV all day makes other people's lives worse, then now you're talking about morality, right? Or ethics or communal living in a society. That's not a question of meaning in life. Meaning in life tends to be very personal and therefore to me is completely relativistic. I don't think that there's any objective answers. But it's still interesting to talk about because even if I say meaning in life is relative and I'm able to come up with it myself, that doesn't tell me how to come up with it, right? There's still a lot of work to be done. Like, what gives my life meaning? How do I attach meaning to it as a personal question can be a very hard one. That's why we debate different possibilities. That's why I think we should be open to inspiration from many different sources and take the best of what we hear from all sorts of things, whether it's religious texts or fiction or movies or our friends or our inner contemplations or whatever it is. Whatever thoughts can lead you to a life that you personally find more meaningful, good for you. That's great. Jeff B. says, can you talk about why the Schrödinger equation needs to be complex valued and why the phase is important in understanding how a wave function behaves? So it's not the Schrödinger equation, technically, that needs to be complex valued. It is the wave function, the quantum state. The easiest way to represent the quantum state of a system is as a vector in a Hilbert space, a complex vector space. By complex vector space, we mean vector space is just something where you have a bunch of elements and you can add them together and you can scale them by multiplying by some numbers, right? You can make a vector longer or shorter by multiplying it by a number. And in the case of a complex vector space, you're allowed to multiply by complex numbers, real plus imaginary part numbers. And you don't actually ever have to use complex numbers. You can always rephrase complex things in terms of real things. If I say that I have a complex number, a plus ib, where a and b are real numbers and I is the square root of -1, then I can always just use new notation where I rewrite everything in terms of a and b and some rules for multiplying them together and so forth. It's awkward. It's just not very nice. And it's not very elegant. It's just much easier to bite the bullet and use those complex numbers. So that's what we do. But like many other mathematical things, it's a choice based on convenience. So the real question is sort of why is that the most convenient thing? Why does quantum mechanics make complex numbers the most convenient thing? And people have tried to answer this question, but I kind of think that this is the kind of question that might never have a completely satisfactory answer, because what kind of answer could you possibly get, right? You're going to say, well, the reason why the wave function is complex is because ... And then you're going to invoke some other principle or fact that you want to be true. Stephen Hawking wrote a paper about this, actually. And he had, something based on time symmetry and path integrals and stuff like that eventually led him to say, and that's why the wave function has to be complex. But you're invoking those other things, right? You're assuming some other things that then lead you to say that the wave function is complex. In the way that I like to think about quantum mechanics, the complexity of the wave function is simply a starting point, right? It's the first ingredient, one of the first ingredients you put in. Quantum states are represented by vectors in a complex vector space. That's one of the beginning points, one of the axioms of quantum mechanics. So I don't try to explain it. It has consequences. For example, the wave function can evolve. Let's say you have a wave function a vector that is of unit length. Right? So its length is 1. That's what a good wave function does. And then you sort of take the components and you can square them to get the probabilities. So they will add up to 1 just by Pythagoras' theorem, right? But you want it to evolve without changing the fact that its length is 1. If you think of a wave, an individual wave oscillating up and down, it can oscillate up and down, but that means it has to go through 0. If you have a real valued number that goes between -1 and +1, it goes through 0 on the way. But a complex number can oscillate from -1 to +1 without going through 0. Its magnitude can stay equal to 1 by going e to the I omega t, where omega is the frequency and t is time. So that's basically saying you go from -1 to I to +1 to -I to -1, etc. And that turns out to be extremely useful for what actually happens in quantum mechanics, for interference effects that maintain the probability rule, all that stuff. So the fact that the wave function is complex is very important in quantum mechanics, or that it's conveniently represented using complex numbers is very important, but I'm happy to just take it. as true and go from there. If you prefer something else that you want to use to derive it, that's also okay. One of the things about axiomatic systems is there's often different ways to write down the fundamental axioms and derive them from each other. I'm going to group two questions together. One is from John Morgan, who says, in a prior AMA, you mentioned that should human lifetimes be extended indefinitely, you feel like you've got a good several thousand years of things to keep you occupied and interested in staying alive. So assuming at one point you'd undertake a distinctly different career, what would be your first next gig? And Paul Hess says, do you imagine a phase of your life where research will not be a central activity around which all of your other activities orbit? Last month's AMA question about a life of thousands or more years got me thinking about how some of us seem to wholeheartedly become different people in different phases of our life, while others seem to be the same core person with the same basic habits as they travel through different parts of their lives. I don't think either of these two is better or worse, or even as pure as described, but I would love to hear your own self-concept of how you might change over the years. So it is a good question that I have not really put a lot of thought into on the basis of assuming that my life will probably not last thousands of years. I do feel very much in favor of this idea that your life should change. Again, now we're talking about a meaningful life in a very personal sense. So when I say, I think your life should change, what I really mean is I think my life should change. You can do whatever you want. That's fine, as long as you're happy and fulfilled. But I do think that I enjoy doing different things at different phases of my life. Having said that, obviously, I'm not doing radically different things. I've been, sticking around universities basically my whole adult life. So I've not completely flipped things over and changed things. Within the university, I've changed specific things that I do, but I'm not, suddenly taking to sea in a sailboat or anything like that. If I did think that I was going to last for thousands of years and be, healthy and aware the whole time, I could easily see doing something very, very different. But I guess, sorry, I should remove the words very, very from that statement. I could easily see doing something different, but the kinds of things that I would see myself doing are arguably in the same kind of universe, the same universe of trying to be creative and intellectual and learn about the world and understand the world. I mean, I could easily see being a history professor or something like that, right? Something slightly different would be more in the creative arts kind of thing, in the arts rather than the sciences, whether it be writing fiction, which is probably the easiest transition I could imagine. Music is something that I really like, but I'm terrible at. So I don't think I could make very much of a career doing that, or acting for that matter, likewise. But who knows? If I knew I had thousands of years to practice, maybe I could become better at it. So I think that, if I had a guaranteed thousands of years lifespan, I would like to sort of do a journey through various different ways of thinking about the world, learning about it, creating new things. That would be my very vague roadmap for what actually happens. But, on the other hand, maybe I'll just end up playing poker and making money that way. Jim Murphy says, I'm reading Quantum Field Theory as Simply as Possible by Tony Z. In one dimension, the concept of a wave packet being produced makes perfect sense to me, since it's just like a little signal traveling down a wire. But when we move to two dimensions, I don't see how wave packets could be produced. Thinking about the surface of water, for example, when a pebble gets thrown into a pond, the ripples spread out in all directions. I don't see where in all this the packets get produced. Or in 3D, when you scream, the sound gets spread out in all directions. So there is a new book that just came out by Anthony Z, my former colleague at the ITP in Santa Barbara, who is a very respected, well-known theoretical physicist and also the author of a bunch of very good books, including a standard, not really standard because he's a quirky writer, but a more or less straightforward quantum field theory textbook. And Tony has a new book out called Quantum Field Theory as Simply as Possible, which at first when I saw it, I got a little worried because it was uncomfortably close to what I'm trying to do in volume 2 of the biggest ideas in the universe, explain quantum field theory to a broad audience. But then I actually bought it and looked at it, and my worry went away. Not because it's not good or worth reading, but because his approach is so completely different to mine that there's essentially no worry that there's going to be overlap there. For one thing, his book is way longer than mine would be. And even though, he does work very hard to not overload you with equations, etc., he is going through sort of the standard curriculum that you would learn to do quantum field theory. Whereas I'm trying very hard to reimagine things so that you can get the essence of quantum field theory without it just being a quick and dirty version of a standard quantum field theory course. Anyway, I recommend the book very much if you want to check it out while you're still waiting for volume 2 of The Biggest Ideas to come out. So the question is about wave packets, and I think this is a very good question to ask, and I might give you a different answer than you get elsewhere, so feel free to ask other physicists to do a reality check here. I think that, Jim, your intuition is completely correct. Generally, in the world of wave phenomena, when you clap your hands and sound comes out, or when you throw a pebble into a pond and it ripples, those waves move out in all directions. That generally is what happens, and it also happens in quantum field theory or in quantum mechanics. And then we have this question, why is it that what we observe looks like particles leaving tracks that look like trajectories, not big puffy waves moving out in all directions? Of course, the answer to that, it is because the particles are interacting and decohering, and you're seeing part of the wave function, and you can actually do a calculation that says if you have a spherically expanding wave function and you put it in something like a bubble chamber or a cloud chamber, right? These are detection apparatuses that can let you see the track of a little charged particle moving through them. Well, very quickly, the wave function bumps into this cloud chamber that you're in, and it is essentially measured, right? It decoheres. The universe branches, the wave function branches into many different branches, each of which describes the particle having bumped into the cloud chamber at some particular point with some particular momentum. And then if you follow the subsequent evolution, that little point with a certain momentum is moving along more or less the straight line that you see in the cloud chamber, or a curved line if you're in a magnetic field. So I think that the answer to your question is the real world almost never has wave packets freely moving in empty space. The real world has these big spherical waves. Like I think this is an accurate statement. When you detect a photon from a distant star or galaxy, before you detected it, its wave function was spread out over millions or billions of light years, and you just collapsed that wave function by detecting it. And you're like, well, that seems a little lucky that it collapsed right down to me. But there's a whole bunch of other wave functions which you're not detecting, which will eventually be detected as moving in some other direction. So it all balances out in the end. The wave packet idea is a convenient fiction for quantum field theorists. You can convince yourself or let yourself believe that quantum fields are acting particle-like by pointing out correctly that I can always construct a little vibration in a quantum field that is confined to a small region that looks like a little packet, and that kind of acts particle-like. But you're right, that doesn't automatically happen. It sort of temporarily happens while things are being observed, and that's why we see tracks in detectors and things like that. But out there in empty space, the waves move out in all directions. David Maxwell says, imagine you wake up tomorrow and you are 40 light years from Earth, alone, with no chance of company, but with ready access to the entirety of human writings, medical technology that will keep you alive to 120, and the ability to send messages back to Earth with no faster-than-light trickery. How do you spend the rest of your life? So I had to parse this question to see exactly what David was getting at here. I think that what is being gotten at here is, in this circumstance where I have, I'm healthy, I'm good medical technology, and ready access to the entirety of human writings, I could continue to write, I guess, podcast. The question just said, send messages back to Earth. I can't interview anybody, though, so it'd be nothing but solo podcasts. But I could continue to write. I could write books and things like that. I could do research in some sense. I'm not sure if my ready access to the entirety of human writings gets updated. Probably not. It's probably just the access to the entirety of human writings as of the moment that I appeared. The question then is, two questions. One is, would I think I have anything interesting to say? So one thing is, of course I would, because suddenly I woke up tomorrow 40 light years away. That's a very interesting story to tell. I want to think about that. And then later on in the question it says there's no fast and light trickery. I'm not sure how we can reconcile those two ideas. But there are things I would still want to say. I guess the flip side of that is I would never know what people thought about what I was writing, right? There'd be no comment section. There'd be no sales figures. There'd be no talk that I gave with questions and answers afterward or letters or anything like that. Would it still be worth doing research, writing, etc., if I felt that I could send my work back to Earth, but I never knew what the response was? I think that you would get a lot of readership because you're stuck 40 light years away. That's a pretty unique thing, unless there's a whole bunch of better writers than me that are also stuck 40 light years away. So I think that I would still, write. I would still try to think of things and write them down and, maybe be better if you didn't know what people thought about your work. It's obviously overall worse because you don't get constructive feedback, but maybe there's a little bit of less worry about the less constructive feedback that sometimes you get. So otherwise, are there other things I would do? Yeah, I would amuse myself in some way. Maybe I would finally learn to play some musical instrument. I'm not sure. Sid Huff says, I understand that the U.S. National Institutes of Health has tentatively planned to stop using measures of researchers' expertise and their institutions as part of grant evaluations. Supposedly, this is to reduce reputation bias in grant decision-making. Do you think that this is an appropriate step to take? And if so, would you approve of the National Science Foundation adopting the same measure for physics grants? So let me personally say I have no idea whether this is true or not, that the NIH is doing this. This is just an assumption embedded into the question. And I would say no, I do not think this is a good idea. There are certainly, it was amusing to me when I first realized that philosophy papers, technical journal research papers, are most often reviewed blindly. In other words, if you're the reviewer, which I've been a reviewer for some of these papers, you're not told who the author is or where they are. You're just given the paper. If you want to cheat in the modern world, you can very often Google the title or the abstract or whatever. But I found it's actually a really useful exercise to not do that, to take it seriously. And sometimes you probably can't, right? Like not everyone puts their papers online. Some people do, some people don't. It's good for the soul to actually read the paper without any idea who the person is and what they're getting at. And one thing you find is that sometimes people are not very good at making clear what they're getting at. And sometimes it'd be useful to know, oh, I know what this person is getting at because they've been getting at this for the last 40 years. I don't know if it would work for physics papers. It barely works for philosophy papers, honestly, but I think it's a good motivation. The aspiration is in the right direction. I don't think that's true for grant proposals. In fact, I would say the opposite should be true. One of the things I've long thought is that there should be basically two kinds of funding that funding agencies do. One kind is, how good has your research been? If it's been good, we'll give you money. You don't even have to send in a proposal. Like if you want money and your research has been good, we will give you the money because you're a good researcher. And then maybe, you get renewed every 3 years. And if in those 3 years you didn't do anything, you get a warning. The funding agency says, we sure hope you're really cooking up a blockbuster there because you haven't done anything for the last 3 years. And in the next 3 years, if you still don't do anything, you're cut off. But maybe you've taken the time to actually do a blockbuster, which is hard to do. The current system, where you have to pretend to, as a theoretical physicist, there's an ongoing joke, a long-running joke about theoretical physicists writing grant proposals, because the grant proposals always want you to explain exactly what you're going to do. If you're building an experiment or doing observations, that's a possible ask. You can tell what your plan to build is. If you're a theoretical physicist, you have no idea what you're actually going to do for the next 3 years. You can say, I'm interested in these problems, but if you knew how to solve them, you would have solved them already. So very often you end up kind of lying. You basically take what you have most recently done and pretend to have not done it yet and say, I plan to do this. And then you can be very specific about what you plan to do because you've already done it. And there's this weird kabuki theater back and forth that people go through. And it's a tremendous waste of time. People put a lot of effort into writing grant proposals. The acceptance rate is not very good. If there's someone who has clearly been doing super good work for over a decade, why are you putting them through this, pretending that they're going to do something that either they've already done or they're just guessing at? It's just a complete waste of very, very, very valuable resources in my mind. So I think that established researchers should be able to just get money on the basis that they have been doing good work without trying to guess what they're going to do next. And then there should be another track, right? That's one track. The other track is you're not established, or you're an established researcher, but you're planning to do something completely different, right? So new territory grants. And there, it would make perfect sense to get rid of information about expertise or institution or anything like that, because you're really proposing, I would like to do this new thing. And maybe it's because you're young and it's the first thing you've ever done. Maybe it's because you're older and you're trying to do something new. But in any way, you're not being evaluated on your recent accomplishments. You're being evaluated on the cogency of your proposal. That's a different kind of thing. And I think that's also very good, but it shouldn't be the only thing. I will say, for the cynics out there, I've sat on plenty of grant review committees, right? Where you, for the DOE, the Department of Energy, or for the National Science Foundation, or for the Guggenheim Foundation or whatever, you read these proposals and you decide who to give money to. And in my experience, there's been plenty of very high reputation people who did not get funding from the committees I was on because they had kind of phoned it in their grant proposal, right? And I felt kind of guilty about it because I bet they will do good work and they probably deserve money to do it. But given the criteria we were given, their proposals were not as good as some young unknown person, and so the young unknown person got the money. And that I think that the people who have not been in that situation, being on the grant review committee, probably underestimate the seriousness of how people who are on those committees really address their task. I've heard similar things about juries, in criminal procedures. People are always surprised that the people who are sitting on the jury actually take their job really seriously. And they, once you're in that situation, it's kind of an argument for sortition as a way to pass legislation. Like once you're in that position of responsibility, you actually kind of try your best, whatever that is. Maybe your best isn't that great, but you try your best to be free of bias, etc. So I don't think that particular move on the NIH's part sounds very promising to me. No. David Harper says, as a professor, do you think the student as customer mentality is a real thing at universities, and do you think it could possibly be a good thing? What onus should be placed on students? I am not an expert in educational policy or the current American university, etc., so I can only talk about my own personal experience. And my own personal experience is I have never seen that philosophy, that mentality at all. None of the places I have been have thought of their students as customers. In fact, I don't know how people envision what actually happens in universities. But to a very large extent, faculty members do whatever they want. Faculty members teach the courses they want, or at least, maybe the department, which is their other faculty members, assigns them certain courses to teach, but they do so using the texts that they want, giving the exams that they want, handing out the grades they want, etc. There's always one or two stories that get attention of like, oh, this person was fired because they're a tough grader or something like that. But Or on the other side of things, like these people were giving passing grades to all the players on the basketball team or the football team or something like that. So there's these stories about that, but it's very, very far away from representative of what typically happens. I've been teaching courses, taught 2 courses last semester. No one in my department knows what grades I gave or what texts I use or anything like that. The individual faculty have enormous autonomy in this kind of situation. So I don't know. I don't know what impact it has had other places, on other people, etc. I look at the relationship between students and faculty as kind of a complicated, nuanced thing. The students are paying to get an education, and they're sort of putting the responsibility in the hands of the professors to put them in a position to get that education. And at the end of the day, it's the student's responsibility to take advantage of that position that they're put in. You cannot force people to learn. Some people, like, why do people cheat, right? If you thought that the goal of being at a university was to be educated, to learn things, cheating on exams or papers is completely counterproductive. You are not forcing yourself to learn the things that you learn. Of course, there are many, many students whose goal at university is not to get an education, but to get a credential. They want to go to medical school or law school or just get a job or whatever. Fortunately for me, those students are not ones that I interact with very much. Maybe there are different parts of the university where they're all over the place, but then you'd have to talk to someone in that position. I really can't say. David Dubrow says, why is it that a book always seems to be used as the quintessential example object thrown into a black hole when discussing the black hole information paradox? It seems to me that the content of a book has relatively little information compared to the book itself as an object with a very specific structure, irrespective of the actual ink mark on its pages. Yes, of course, you're completely correct. We could throw anything at all into the black hole, and the point is, what is the complete specification of the quantum state of the thing you're throwing in? That's the information that is relevant. In that sense, the difference between a book with blank pages and a book with text on it is infinitesimally tiny in terms of how much information content there is. But it's an example, like you said, right in the question. It's the quintessential example object. No one is really throwing things into black holes. We're using examples to drive home the idea that information exists. It's going into the black hole. How do you get it out? It's easier for the typical person who is not a scientist to envision the existence of information as the text on the pages of the book than the complete quantum state of all the atoms and molecules of which the book is made. Technically, it's the latter that really matters, but the former also matters, and it's a more vivid example, so we generally use that. Noble Gas says, has Low-Schmidt's paradox been resolved to your satisfaction? If so, briefly explain how. Probably should have put this one earlier when we were talking about the past hypothesis, but Low-Schmidt's paradox, you can really read all about this in my book, From Eternity to Here, if you want both the history of it and the resolution. Low-Schmidt's reversibility puzzle, as I would like to call it, was a challenge to Boltzmann when Boltzmann was trying to first explain the second law of thermodynamics and entropy in terms of arrangements of atoms, right? We already knew about entropy. That was Clausius and Carnot before him. But Boltzmann and Maxwell and others came up with a definition and understanding of what entropy is in a world where things are made of atoms. Namely, the entropy is a way of measuring how many different arrangements of the atoms there are that satisfy certain macroscopic criteria, maybe what you see when you look at it or something like that. And Boltzmann basically said, entropy tends to increase because there are far more ways to be high entropy than to be low entropy. So if you start in a low entropy configuration, the overwhelming majority of trajectories will take you to a higher entropy configuration. And Low-Schmidt, who was actually Boltzmann's old professor from his university days, pointed out completely correctly that that can't be the entire answer because you're sneakily asking the question, if you begin with low entropy, what is likely to happen? But you could be asking the question of all the trajectories in the universe, not conditionalizing on starting at low entropy, but of all the trajectories, what is likely to happen? And the answer there, because the underlying laws of physics are presumed to be reversible, the chances that you will start in high entropy and spontaneously move down to lower entropy, in apparent contradiction to the second law of thermodynamics, are exactly as big as the chances that you would have started randomly in the low entropy state to start with. Said another much more simpler way, there's a precisely equal number of trajectories going from low entropy to high as going from high entropy to low. It has to be that way because the laws of physics are presumed to be reversible. That's Low-Schmidt's reversibility paradox. And it's one of many different versions of the idea that you cannot start with time-symmetric laws and derive time-asymmetric behavior. So the resolution is you need to put in something time-asymmetric. And the answer is you put in the assumption that the early universe started with low entropy. That's the past hypothesis that we started the whole AMA talking about. The past hypothesis is a time non-symmetric assumption about low entropy at initial conditions, and there is no analogous assumption of any sort for the future. It's only the past hypothesis. There's no future hypothesis. So that breaks the symmetry and resolves the paradox. Casey Mahone says, do you have any mindless or repetitive hobbies you use to help you relax? For instance, I enjoy knitting. It depends on what you mean by mindless and repetitive. Probably the closest I would come is just playing mindless repetitive games on the iPad for a few minutes before going to bed at night or whatever, right? Solitaire or poker or backgammon or, very simple things that have nothing to do with whatever it is I've been thinking about in research or book writing or podcasting for the day. But I wouldn't even raise those to the level of a hobby. I don't really think about it that much. So probably the answer is no in the conception that you have in mind there. Brendan says, do you think the difference between being agnostic and being an atheist comes down to the probability one gives in there being a God? I know you and other carefully thinking atheists acknowledge there is a very low probability of God existing, but still are okay with using the term atheist instead of agnostic. So I don't want to worry too much about arguing about the definitions of these words. Like, we should agree on definitions and then argue about substance rather than arguing about definitions. Roughly speaking, atheists are people who think that they are confident enough to say that God doesn't exist. That doesn't mean it's with 100% metaphysical certainty. I can't say anything with 100% metaphysical certainty. But if I look outside and I say it's not raining, I could be fooled. There could be an evil demon. Someone could put a screen outside my window that is tricking me or something like that. So I'm not 100% sure, but I'm not going to include all of those caveats in my statement. I'm just going to say, yeah, it is not raining right now. And I mean that at some confidence level, 0.999, whatever. And I have exactly the same feeling about the existence of God. Agnostics would like to say that we just don't have enough information one way or the other, so I will not pass judgment on whether or not God exists. And roughly speaking, that probably corresponds to a credence in God existing that is bigger than 0.0001, but smaller than 0.99 something, okay? But, I do think that that's the respectable way of doing it. So I think that having a credence in the existence of God, whatever it is a perfectly respectable thing to do. There is a strategy sometimes used by agnostics that I think is not reasonable, which is to somehow carve out the existence of God as a question that is somehow a different kind of question than whether it is raining outside right now. To say that the existence of God is something that we can't have evidence for or against, therefore I shouldn't have any high or low credence in it being true. I think that's just wrong. I think that's just mistaking how we generally come to our credences. As I alluded to before, science is a tricky kind of subtle process of going back and forth between model building and evidence. And even if you don't have direct evidence for or against the existence of God, you can still evaluate that claim on the basis of perfectly ordinary scientific reasoning. That's a theory about the nature of the universe, the existence of God. How does it fit the data? If that theory were true, would you expect the universe to look that way? If that were not true, how would you expect the universe to look? Plug in Bayes' theorem, all the ordinary things. So the kind of agnostic reasoning that somehow tries to treat the existence of God differently than other big questions about the universe, I think is wrongheaded. I think it's treating God, as a different category than the question really belongs to be in. And therefore, I would argue against that. I think that that's not just a matter of personal credences. I think that's a logical mistake there. Ollie Whittle says, my 6-year-old son and I like listening to your AMAs while driving. He has the following question. I understand that black holes suck everything in, but what is a white hole? What does it push out? Emerson Whittle, age 6. So thank you, Emerson. I enjoy your question. I'm glad you were able to ask it. I hope it's not you who are driving. I hope it's your father, Ollie, who's doing the driving while you're listening to this. So first, it's not precisely exactly true that black holes suck everything in. And this is, an opportunity to sort of get this right. Black holes are regions of space-time that have a gravitational field, so you can orbit them, like you can orbit the sun, etc. And they have the feature that if you enter that region, you can never leave, okay? You don't have to enter that region. You can literally just stay orbiting the black hole. So the Earth is orbiting the sun right now. If tomorrow we took all of the mass of the sun and squeezed it down and made a black hole, the Earth would still orbit in precisely the same way. It would not get sucked in. So it's better to say that black holes are one way. You can go in but not come out, rather than imagining some sucking force that is different than the ordinary force of gravity. It's just ordinary gravity in action here. A white hole is completely hypothetical. We have no evidence that white holes exist, but technically speaking, a white hole is just a black hole played backward in time. So if you imagine making a black hole by some reasonable physical process, like a large star reaches the end of its life, its fuel gives out, it collapses, and it makes a black hole, okay? You could imagine playing that entire process backward in time. You would start with a white hole. It would throw out all of the matter and energy that would make a star, and then you would have a star there. Now, that's implausible for all sorts of reasons. It is literally violating the reversibility of time, right? Or, it is only possible if you think that time is reversible, but macroscopically in the real world, it is not. There is an arrow of time. For white holes to exist, entropy has to be able to go down, which it's not. That never ever actually happens in the real world. So I think that the right way to think about white holes are as hypothetical mathematical constructions, but nothing you need to worry about existing in the real world. The one little exception to that is that in some sense, our whole universe is kind of like a white hole. It started with a singularity, and at least that's the prediction of classical general relativity. The Big Bang singularity is kind of like the past singularity of a white hole, the time reverse of a future singularity in a black hole. But there's no outside world into which we're being spit out, so the analogy to a white hole is not perfect even for the universe as a whole. Josh Charles says, it blew my mind when I learned that the information in a black hole is proportional to its surface area and not its volume. My intuition wants to interpret this as a changing of the geometry of space-time such that it doesn't have a volume. If space is emergent, is it possible that this is indicative of such a modulation? And if not, would it be possible to have multiple geometries of space-time within the same universe? I'm not sure I'm going to give a satisfactory answer to this question, but I'll try to say some true or at least plausible things that might help you think about it yourself. First, when people say the information in a black hole is proportional to its surface area, that's a way of talking about the fact that the entropy of a black hole is proportional to its surface area. That's really what is going on. And by itself, that wouldn't be weird at all. If you just have an ordinary condensed matter system. By condensed matter, I mean something we literally make out of, atoms and molecules, and you put it in a lattice, okay? So you have like some two-dimensional sheet of graphene or spins or something like that, okay? And you put that condensed matter system, that two-dimensional sheet, into its lowest energy state. So it's in its vacuum state. There's nothing going on, but there's a quantum state, and there are atoms and molecules, and they can be entangled with each other and whatever, okay? This is a very typical thing that condensed matter physicists look at in the lab. And you consider some subsystem. So you take this two-dimensional sheet and you, like, in your mind, and not with a knife, but in your mind, you carve out a little region, okay? And like I said, the atoms and the quantum degrees of freedom in that region can be entangled with the atoms outside that region, and therefore that region has an entropy. And guess what? The entropy of that region is going to be proportional to the area of the region that you just cut out. Why? Because the entanglement is mostly short-ranged. Atoms are going to be highly entangled with ones nearby, not so entangled with ones far away. And so all the entanglement that you're breaking by cutting out the region is located near the boundary. And the area of the boundary gives you the total amount of broken entanglement and therefore the total amount of entropy. So that's a long-winded way of saying the fact that the entropy of something is proportional to its area, not its volume, is not surprising. We absolutely have very ordinary, non-gravitational, non-black hole examples of that. What makes it surprising, it's not really surprising at all, but what makes it surprising in the black hole case is that it's supposed to be a maximum entropy configuration. You're not supposed to be able to, and I think it's true, you can't fit more entropy into any region of space than a black hole has. That's surprising because if you take our condensed matter system, remember I said it was in its lowest energy state, but its lowest energy state is not its maximum entropy state, right? If you heat it up, you can get a lot more entropy in that system. And in that case, the maximum entropy that you can have in the region that you cut out is proportional to its volume. So the weird back and forth is, if something is in its vacuum state, it's very natural for a subsystem to have an entropy proportional to area. If it's in its maximum entropy state, you'd expect it to have an entropy proportional to volume. A black hole is a maximum entropy state, but it still has an entropy proportional to area, not to volume. Okay, that is the very complex back and forth, but pretty respectable set of intuitions that we might have about this. And this is what led people to invent the holographic principle, Leonard Susskind and Gerard 't Hooft and others. The idea that all of the information is somehow literally on the horizon of the black hole, or at least can be thought of as being there. Okay, all that is background to the actual question. Josh wants to interpret this as a changing of the geometry of space-time such that it doesn't have a volume. Well, you know, we don't know is the first thing to say. We're speculating here. We've never been close to a black hole, much less inside it, doing delicate experiments or anything like that. So everything I say is conjectural here. But what you're conjecturing is something very similar to the principle not of holography, but of black hole complementarity. This is another idea that came from Susskind and others. And the complementarity idea is that what the black hole is, the physical system that you should think of as the black hole, depends on how you look at it. There is a way of looking at the black hole which you can roughly associate with someone falling into it. And there, it looks like a three-dimensional region of space, four-dimensional region of space-time, with a volume and everything is completely normal when you're inside, except you're going to be crushed in the future, okay? Whereas from the point of view of the outside observer, and that initial infalling point of view is what we would learn about in our classical general relativity textbook. That's what Einstein's equation would teach you about, would seem to imply. But the complementarity idea is that from the perspective of an outside observer, it is as if the horizon of the black hole is the black hole, that all of what is happening in the black hole can be thought of as living on a membrane. The classical version of this is called the membrane paradigm. This is sort of the quantum mechanical version of it. The complementarity idea that there, from the point of view of an outside observer, a black hole is a membrane with a certain area and a certain number of degrees of freedom. If that's what you mean by saying there's a changing of the geometry of space-time, then yes, that is what is going on. Multiple geometries of space-time within the same universe, yes. But again, it's a very careful statement. You can't say the black hole is three-dimensional or two-dimensional. It appears one way or the other to different observers or from different perspectives. It is some quantum state. Right? That's the essence of it at the end of the day. So geometries of space-time emerge out of that from some certain perspective that you're looking at. Tarun says, in your book, Something Deeply Hidden, you describe how Schrödinger's cat, being either dead or alive, would rapidly decohere into two branches due to interactions with the environment before the observer has even looked inside. But if the purpose of the box is, in a sense, to avoid any interaction with the environment, even if that's not possible in practice, wouldn't the cat indeed be in a superposition of states as far as the outside world is concerned until the box is opened? Well, I think the short answer there is it's difficult, even like you say, even if it's not possible in practice. But practice matters for these questions. It is really not possible in practice. Like the environment in the box is literally like the air and the photons in the box, okay? So you'll only have a dead cat if there's no air in the box. So that's a problematic thing. But even if you forget about that, even if you somehow imagine that the cat stays alive, even though there's no air there, a cat gives off radiation, right? A cat has a body temperature that gives off infrared light, and instantly, a nanosecond after you start the experiment, there's an environment because the cat has given off radiation differently depending on whether it's in one position or the other. All of which is to say, the whole point is once you get a system that is as macroscopic and messy and high temperature as a cat, it is really, 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 really hard to avoid it interacting with an environment and branching the wave function. So hard that it never happens. And, the point of decoherence and the many worlds interpretation is to explain what actually happens. That's why in David Wallace's book about many worlds, it's called the emergent multiverse. Because it is emergent. You can always just talk about the wave function and avoid branching, just like you can always talk about the gas in the room as being a bunch of atoms and molecules. It's way more convenient to talk at a higher level of description where there's smaller number of entities that you're concerned with. And at that higher level, there are branches of the wave function. So we're actually trying to solve in practice problems here. So to say, well, this is not possible in practice means who cares? That's not what we're interested here when we do the many worlds interpretation. If you are super interested in things that are not possible in practice, then I would just say, just have the Schrödinger equation, just solve it. Don't ever talk about branches. You're Laplace's demon. Congratulations. Malta Ubel says, the other day my daughter, 6, was complaining over breakfast that sometimes when the teacher called on her, she'd not always know the answer to their question. I somewhat unhelpfully quipped, if in doubt, just answer your teacher with, that is because of the second law of thermodynamics. But then my wife dropped in, that isn't right for math questions, which is very fair. My question is, which classes of answers do not have the second law of thermodynamics somewhere in their causal chain? I think that I could be cheeky and try to claim that every question does because someone came up with the question and that person who came up with it is embedded in the second law of thermodynamics. But I get the point of the question. And I think the simple answer is, does the issue being addressed have time reversibility? Is the answer the same whether you run it forward or backward in time? Even math questions have an element of interestingness to their reversibility. That's the whole basis of the fact of P versus NP and prime numbers, right? To prime factor a big number is difficult. To take a big number and discover its prime factors is difficult, but to start with some prime factors and multiply them together is easy, right? So doing it one way in time is actually easier than doing it the other way of time. But of course, you can do it either way, and the actual for either multiplying or factoring, you can do those things either forward or backward in time. So it's not technically time that is getting in there. So I would just say, think in the back of your mind, could I do exactly the same thing backward in time? And would it look weird? Would it require, would someone notice if I did this and I made a movie of it and I played the movie backward? Would people notice that something funny was going on? If so, then the second law of thermodynamics is definitely playing a role there. Chris Shipton says, is it possible to slow the spin of a black hole down? From the podcast that mentions spinning black holes, it seems like the spin always increases when something is thrown into the black hole. Yeah, it's absolutely possible. I mean, the spin of a black hole has a direction, there's an angular momentum, and you just throw something in moving the other way. In other words, for real black holes, generally, the stuff that is falling in is in the form of an accretion disk, and that disk is rotating in the same direction as the black hole is, so the black hole gets more angular momentum when that stuff falls in. But if by hand you just threw something in the other direction, it would absolutely slow down the spin of the black hole. In fact, that's exactly what happens in the Penrose process. The Penrose process, named after Roger Penrose, former Mindscape guest, is a way of extracting energy from spinning black holes by slowing down their spin. Simon Carter says, I was re-listening to your Christmas message from a few years ago titled The Screwy Universe. We were talking about birefringence and mentioned an experiment had confirmed this to 2 sigma, and you were waiting to see if further details would either rule it out or further confirm. Has there been any further update over the last few years? Yeah, this is something that takes time. There have been updates, but they're very slow and tentative. There's still updates in the sense of analyzing the existing data, but trying to do better and better data analyses of it. And my impression, I've not followed this super duper carefully, but my impression is 2 things. The claimed detection is still there. Maybe it's even arguably closer to 3 sigma than to 2 sigma. It's a small detection. It's saying that, so for those of you who don't know, what we're talking about is the possibility that light, polarized light, as it travels through empty space over cosmic distances, has its polarization vector rotated a little bit. And what we're talking about here is literally 1/3 of a degree as it goes from the cosmic microwave background to us. So a very tiny amount of rotation. And this is an effect that you would not expect to see in ordinary physics. You can get rotation of polarization. That's very easy. Faraday rotation is an example, but that has a very clear signature because the amount of rotation depends on the wavelength of the light. And my first ever published paper with George Field and Roman Jakiv looked at how to constrain theories of electromagnetism which violated Lorentz invariance, which picked out a preferred direction in the universe, in space-time. And the particular thing that we looked at was a very easy, straightforward way of violating Lorentz invariance, and it predicted cosmic birefringence. And I typed in some data and fit some numbers and did some least squares and showed that it was consistent with 0 birefringence in the real world. But our limits were like 10 degrees of rotation. Now they're down to the 0.3 degree level. They've come a long way. I also pointed out after the discovery of the accelerating universe that dark energy could do this. Certain candidates for dark energy, axion-like dark energy candidates, could lead to this cosmic birefringence. So my personal happiness would be maximized if this is true, since I was there on the ground floor predicting this cosmological birefringence. But it's very, very difficult to detect, and it's easy to have a small effect go away. So I'm still going to wait until we have more data before I get very excited about this. The other thing, in addition to the fact that it's still there, is I believe, and this is something I'm, again, not completely an expert on because I haven't been following it carefully enough, but my impression is, well, you have to worry about foregrounds, right? When you're looking at polarization in the cosmic microwave background, it's in a very, very tiny numbers that you're looking at. And our galaxy is full of dust that can lead to polarization, that can confuse you, etc. And my impression is that what you do is you try to, you do your best to take into account the fact that the galaxy is there and the galaxy has dust in it, etc., and remove that from the data. But to be sure, to check that you've done it correctly, what you can do is just literally cut out the galaxy. So what you typically do is to try to compensate for the fact that the galaxy is there, but keep the data in the direction of the actual galaxy we live in. But then you compare to what would happen if you just ignored all of the data in the direction of the galaxy, in the galactic plane around us, okay, in the circle of the galactic equator, if you want to put it that way. And there you have less data, right? Because now you're only looking up away from the galaxy or down away from the plane of the galaxy, but at least you're not being contaminated by the galaxy itself. And my impression is that when you do that, the effect becomes less strong from the analysis that has been done. So on the one hand, maybe that's just because you have less data. On the other hand, maybe it's because the effect was originally from contamination from the galaxy. That's why this is hard. That's why it's way easier to be a theorist than an observer, an experimentalist in this game. So trust me, if there's actually any progress to the point where I think that this is probably right, you will hear about it from me. I'm not going to keep that one from you. Brandonk says, you seem to have spent a lot of time and energy focusing on natural philosophy for a while now, thinking not just about the empirical science of physics, but the philosophical underpinnings and implications of physics and science in general. This is no small task, as physics and philosophy of science are each deep, rich, and difficult to master in their own independent respects. Have you encountered any major challenges to your ways of thinking as you've engaged with more of the underlying philosophy, or any kind of shift in perspective? So one thing to say is, I don't think it's that different, honestly, what I'm doing now than what I did before. It's true that my research focus has shifted a bit, but it is still very much the same driving question, trying to understand the nature of our physical world, okay? Trying to use some combination of empirical input and rational thought to come up with the best possible models of reality. The difference in the sort of thinking of it in a more philosophical way is just that which questions you tackle and the methods you use to tackle them are a little bit different, but the same underlying goal is there. So if you care about quantum mechanics, for example, on the foundational or philosophical side of things, you're going to worry a lot about the fundamental ontology of quantum mechanics, whether the wave function is real, things like that, what happens when you make a measurement or it collapses. If you're just a typical run-of-the-mill physicist, you just plug in the formulas and get on with your life. You don't worry about those things. But still, either person is interested in understanding the fundamental laws of physics. Okay, so the question, have I encountered any major challenges, etc.? I wouldn't say that, no. I would say that rather, as exactly should happen if you're doing philosophy or foundational work well, you come across places where there were things that you thought were pretty well established and pretty well figured out, and suddenly you go, oh, wait a minute, that might not be right at all. And I think, to me, like the obvious example is the anthropic principle. And I talked about this over the summer in a solo episode on the philosophy of cosmology. I think we do the anthropic principle very, very badly in cosmology. I think it's a potentially important thing to get right, and I think that physicists are very sloppy about it. The typical physicist way of thinking is there's many wrong ways to get the right answer, but that's okay, because if we get the wrong answer, nature will tell us. We'll do an experiment and we'll find out. But for some of these questions, like the multiverse and the anthropic principle, nature's not going to tell you whether you've done it wrong or not, because you're talking about things you can't observe. That makes it more important than ever to make sure your reasoning is valid, okay? And so I think this is exactly a case where a more philosophical approach is useful, and it certainly changed my views of some claims in cosmology. Nothing major that would really overthrow anything, but things that might end up being important. Michael Monhaupt says, what kind of qualitative influence does gravity have on LHC experiments at CERN? I'm referring both to the Earth's gravity and to the tiny gravity of most particles involved. Well, the tiny gravity of most particles involved at the Large Hadron Collider is completely negligible. No effect whatsoever. There's one footnote there, which is that people speculated that maybe gravity is much stronger than you think at these high energies and short distances. And so that was an idea that led to large extra dimensions and searching for gravitons at the Large Hadron Collider. But it didn't work. They didn't find anything yet. Again, as with any such statement, maybe they will find something tomorrow, but as of right now, as of this recording, they haven't found anything. So as far as we know, the gravitational interactions of particles at the Large Hadron Collider are completely negligible. Now for the Earth, that's a different thing. Obviously, the LHC is, kilometers across. I used to know the number of kilometers, 17 kilometers in circumference, maybe. 17 miles, 30 kilometers maybe? I forgot. It's been a while since I wrote a book, but I did write a book that has all these numbers on it, the particle at the end of the universe. A machine that large sits in the gravitational field of the Earth, and that matters when you're trying to do precision experiments. So in fact, I believe, I'm not an expert because I'm not an experimentalist at CERN, but I remember reading that you could detect the moon using the Large Hadron Collider because the tidal gravitational force of the moon led to very tiny shifts in the instruments that were experimentally detectable. Happily, we already know the moon is there, so this was not a mystery. It was known to be something that you would take into account. So yes, the gravity of the Earth and the moon do matter for those experiments, a tiny, tiny amount, but they're noticeable. The gravity of individual particles don't matter at all. Johannes Funk says, in Chapter 8 of The Biggest Ideas of the Universe, on general relativity, you suggest that all kinds of energy, including things like pressure and stress, contribute to the curvature of spacetime. After recently wrapping my head around the fact that planets in orbit have negative potential energy, as do electrons and atoms, I found myself wondering if this negative potential energy does then also contribute a negative amount to the curvature of spacetime, and thus effectively acts like the presence of some negative mass. Good. So there's two things going on here. One thing is when we say, because I say it too, that planets in orbit have negative potential energy, compared to what? Potential energy is an example of something where the only physical effect in good old classical Newtonian mechanics is differences in potential energy. What the right thing to say is that two gravitating objects that are far away from each other have more energy than if you bring them close by so that their gravitational force is stronger, okay? And you know that that's true because you know that it would take energy to move them away again. So you need to put energy into the system to take two planets that are orbiting each other and separate them. Therefore, there's a negative amount of potential energy there compared to the energy when they're not right next to each other. But the absolute value of that energy is just not even defined in Newtonian mechanics. In general relativity, it's a little bit different because the total amount of energy does matter. The absolute 0 point matters, not just the relative amount of energy. But there's another subtlety, and I apologize if this was not clear enough in the book, but the right-hand side of Einstein's equation, the side that tells you the source for gravity, what is called the energy-momentum tensor, which includes mass and momentum and heat and energy, whatever it is, all sorts of energy densities and pressures and all those things, is really very, very strictly only the energy in stuff, not the energy in gravity or the curvature of spacetime itself. The curvature of spacetime is entirely on the left-hand side of Einstein's equation. So Einstein's equation is strictly saying that the curvature of spacetime is sourced by the energy not in spacetime, but in everything else, in all of the matter and radiation and stuff in the universe. Having said that, the left-hand side does have the curvature of spacetime in it, and it implies that the curvature of spacetime affects itself. It is nonlinear, okay? A little bit of curvature of spacetime can push around the curvature of spacetime, but it's not as simple as negative potential energy or anything like that. It's a complicated nonlinear thing. At the end of the day, what is the most relevant statement I can make for a question like this is empty space is stable in general relativity. In general relativity, there's what is called a positive energy theorem. Under reasonable circumstances, you can't get negative masses just by curving spacetime in weird ways. So when I say that empty space is stable, what I mean is that if there's nothing in the universe but empty space, it can't decay into a positive energy part and a negative energy part, right? Anything you do, anytime you poke empty space to make it ripple or gravitational waves or whatever, you're increasing the total energy. You're never decreasing it. So when you're at that minimum of energy, empty space, perfectly flat, there's nowhere to go down, and therefore everything is perfectly stable. Jim Watson says, for gravity waves, is it a wave in the sense of a harmonic oscillator, whereby there is some restorative force in the space-time fabric, and abrupt perturbances of curvature cause transitory underdamped fluctuations with more or less curvature? Or is it more like an overdamped or critically damped oscillator, and the wave isn't from restorative energy in the fabric itself, but rather the orbital motion of the mass, making periodic changes to the curvature each orbit? Well, let me say, by way of background, that you have to be careful when kind of appealing to these analogies, okay, like oscillators and masses making periodic changes. At the end of the day, these are all words that we are attaching to the equations. In particular, when you think about oscillating things in your experience, you will be tempted by the fact that real oscillating things eventually dissipate their energy, right? They stop oscillating. So you talk about damped oscillations right there in the question. But there's nothing, if there's a gravitational wave in space-time, much like if there is a light wave in space-time, if there's an electromagnetic wave and there's nothing else there in the universe for it to bump into, there's no dissipation. There's no running out of energy, right? The energy is conserved in that thing. So that gravitational wave will continue on forever. But I think to answer the actual thrust of your question, it is a wave in the sense of a harmonic oscillator, in the sense that it is different nearby regions of space-time that are pulling on each other and pushing back and causing that oscillation in exactly the same way that it's nearby regions of an electromagnetic wave that push and pull on each other. So it's a very, very good analogy there. It's just that energy is conserved, so the oscillations never go away. They just move from place to place. Rue Phillips says, what is your perspective on Christian nationalism and its impact on U.S. politics? Is it to be respected as an expression of American ideals, a credible threat to democracy, or something else? Well, I never know quite what to think about these things because the labeling game is very tricky. When you talk about Christian nationalism, is this a self-given label to some group of people? Are there people who are describing themselves as Christian nationalists, or are people who disagree with them describing themselves as Christian nationalists? And I bet that it's both sometimes, but I don't actually know the relative frequency of those things. There is an ongoing debate in the United States about whether or not certain movements can be characterized as fascist, for example, or white nationalist. And maybe not. I think that, there's similarities, differences, whatever. You can have a debate about that. But it's hard to use words like Nazism or fascism or something like that without giving the game away in terms of evaluating, right? Those are so highly charged terms, and maybe they deserve to be. That's fine, but when you call someone a fascist, you're not sort of entering into dialogue with them, right? There's not a lot of people who are self-proclaimed happy fascists out there today, at least not in the United States. So but there is something going on that is resembling that kind of fascism. So what is a more value-neutral term that you could invent? I think maybe this isn't exactly very good, but the closest I can come up with right now is romantic nationalism. The idea of sort of putting your nation ahead of not only other nations, but also the individual citizens inside your nation. The iconography of the over-the-top sort of kitschy portrayals of patriotism and might, military might, and things like that might be accurately labeled romantic nationalism, whether or not you want to be for it or against it, right? Christian nationalism, of course, is part of the actual way that romantic nationalism manifests itself in the United States, as is white nationalism, but in very complicated ways, because there are people within these movements who are not Christian, who are not white, etc. I don't think any of these ways of thinking about politics are expressions of American ideals in any real sense. I think that the ideals, to the extent that it even makes sense to talk about American ideals, I think that those ideals should include a certain cosmopolitan openness to different people, different cultures, etc. I think that's an important part of what makes America America when it is doing good things. Sometimes America does bad things, and then its ideals are not so great. Is it a credible threat to democracy? Yeah, absolutely. I mean, we literally had an insurrection take over the United States Capitol, cheered on by the President of the United States. Like, that's pretty credible as a threat to democracy goes. We had a very, very coordinated effort to overthrow the result of an election. We have an ongoing campaign to put people in positions of power so that next time they can do a better job of it. I think these are super credible threats to democracy, and I would like to take them very seriously because I think that democracy is good, all things being equal. Igor Volotich says, I've recently stumbled across some conversations, including Noam Chomsky, in which he said that science currently recognizes only two concepts, determinacy and randomness, and does not go beyond that. The context was regarding human ability to grasp the world around and about our current limits. Could you even grasp the possibility that there is anything that goes beyond determinacy and randomness, or is this something you wouldn't generally waste your time contemplating? So I answer this question a little tentatively because I didn't stumble across that conversation with Chomsky, so I can't verify that that's actually what he said, that current science only recognizes two concepts. I mean, currently, clearly that can't be exactly right. Current science recognizes plenty of concepts. So what must have been meant is that there is some distinction drawn between determinacy and randomness, and that distinction is purportedly comprehensive, that processes are either determinate or deterministic or random. Yeah, I maybe I'm missing something, but it sounds to me like those are the two options, because the definition of random is not determinate, I think. I'm not sure what the definition of random is. That's the trickiness. That's where some possible scope for thought lays here, because what do you mean by random? Do you just mean that you personally were unable to predict it? Do you mean that it does not depend on in any completely solid way on what happened before in the universe? Or are you doing something a little bit more sophisticated about epistemic subjective approaches to probability and our knowledge? I don't know. So I'm not exactly sure what is meant by randomness there. Not to mention, of course, the fact that quantum mechanics is a classic example of something where we use randomness in our applications of it, but we don't agree on what that randomness is. It depends on your formulation of the foundations of quantum mechanics. But I don't know what would be an example of something that was neither determinism nor randomness. So that's not a very good answer there, but that's the best I can do for that question. Humberto Nani says, I read the following in your book, The Big Picture. The maximum entropy a region of space can contain is higher when the vacuum energy is lower. Can you please explain why it is so? Well, it's basically because the observable universe can be bigger when the vacuum energy is lower. The vacuum energy, we're limiting ourselves here to vacuum energies that are not negative. Negative is a whole different thing. Then you get into anti-de Sitter space, and it's a different story. So the positive vacuum energy story is de Sitter space. De Sitter space is the solution to Einstein's equations of general relativity that you get when there's nothing in the universe but positive vacuum energy. And the higher the vacuum energy is, the more the universe is, the more space-time is curved, right? The faster the universe is accelerating, and therefore the smaller the horizon is. De Sitter space, or an accelerating universe, is characterized by a horizon. That is to say, if you're at any one point in space-time, there's a region inside of which you can see things, light can travel to you, and outside that region, light can never reach you because the universe is expanding too fast. So the higher the vacuum energy, the faster the universe is expanding, the smaller the region is inside your horizon, and therefore the less entropy it's going to have. The formula for the entropy is the same as the formula for the entropy of a black hole. It goes as the area of that horizon around you, and that horizon is smaller when the vacuum energy is larger. Tom B. Knight says, I write science fiction and Mindscape is a constant source of inspiration. I'm working on a new novel and want to know what are the implications of recent advances in nuclear fusion for creating a pure fusion bomb, i.e. one that doesn't require a fission reaction to trigger the larger fusion reaction. So I'm not an expert on the recent advances in nuclear fusion. There have been a couple of questions in the AMAs about them that I have not answered for just that reason. I'm not an expert. I have nothing really enlightening to say about it. But I'm pretty confident in saying that there are almost no implications for creating a pure fusion bomb. The point is that there have been examples recently where fusion has happened. They've made fusion happen, okay? And the question is, how difficult is it to get it to happen? Right now, it's still at the state where you need to put more energy in than you're getting out net at the end of the day. So you're not making overall energy from doing fusion, but you're creating a little bit of fusion. But still, doing that requires a humongous machine, right? An enormous kind of setup with lasers or plasmas trapped or magnetic fields or whatever it requires to make just a little tiny pellet of hydrogen undergo nuclear fusion. So this is just not what you want for a bomb at all, okay? I mean, certainly for a bomb, you want something where you get much more energy out than you put in. You don't want the battery in your bomb to be putting more energy in than you get out of the explosion. Otherwise, it's not a very efficient bomb. And also, you want it to be small. You want it to be able to carry on a plane. So I don't even think that people are contemplating using techniques from controlled nuclear fusion to make different kinds of bombs. Could be wrong about that. Not my area of expertise, but that is my physicist on the street impression there. Anonymous says, in episode 219 with Perry Zern and Danny Bassett, you discuss the idea of spotlighting gaps in your knowledge base to stimulate curiosity and discovery. Asking the right question creates a vacuum that curious minds can't help but try to fill. Are there any lesser-known historical examples that you could share from physics or elsewhere? I don't have any examples off the top of my head. I mean, I kind of wanted to answer this question, but didn't have any good answers for it. But it's absolutely true. Asking the right question creates a vacuum that curious minds can't help but try to fill. The one kind of close example that came to mind is the Fermi paradox, right? Enrico Fermi sitting down at lunch at the University of Chicago and saying, like, why aren't there aliens everywhere? The time scale with which an alien civilization could fill our galaxy with evidence of their existence is much smaller, noticeably smaller anyway, than the age of the universe or the age of the oldest stars or star systems. So if technological civilizations were ubiquitous in the universe, they could have left trails very, very long ago and very, very obviously, and yet we don't see them. So this was a simple question, right? I mean, it's sort of an example of just thinking about something and realizing there's a puzzle that you hadn't appreciated before. And from that, people have put a lot of effort into thinking about it. It has really helped focus our discussions, such as they are, about life elsewhere in the universe. And, maybe that's not a tangible result that has come out of it yet, but you can't have a discussion about advanced alien life without talking about the Fermi paradox, which is a pretty good consequence for a lunchtime table discussion anywhere. Matt Grinder says, the experiment where you send a single photon through a beam splitter and half the waves go to one detector, half go to another detector, seems to show that quantum waves cannot carry energy, since you get a full photon's worth of energy at one detector, not half a photon. Hence, quantum waves must be only probability waves. And there's more to the question after that, but all the subsequent question relies on that little argument that comes at the start. So I wanted to point out this argument is not right. It is not true that you only get, because you get a full photon's worth of energy, quantum waves must only be probability waves. And that can't be true because we have counterexamples, namely the many worlds interpretation of quantum mechanics, where the quantum wave is not just a probability wave, and yet you see the full photon's worth of energy at one detector, not half a photon's worth of energy. Why is that? Well, the answer is you had one branch of the wave function of the universe with a certain amount of energy, and it branched in half, and the whole universe that it branches into, the two universes it branches into, have half the energy each. Roughly speaking, maybe not exactly, but pretty close to half the energy each. And you don't notice that because you yourself are part of that diluting, that thinning out in the wave function of the universe. I've talked about this many times and never necessarily very successfully, but the universe sort of gets skinnier in a very real sense. So it is true that you detected one photon, not half a photon, but that's exactly what you would predict on the basis of saying that quantum waves are not just probability waves, but are actually the physical universe. Andrew Goldstein says, I'm reading Karen Baker's recent book, The Sounds of Life, How Digital Technology is Bringing Us Closer to the Worlds of Animals and Plants. Given your pursuit of physics and natural philosophy and having read The Big Picture, where you discuss at some length consciousness and sentience, I'm curious how you think the growing knowledge of animal and even plant communication might affect our understanding and definition of consciousness. So I don't know. Probably not that much is my guess. I think it will affect our understanding of animal and plant communication and animal and plant cognition to the extent that there is cognition. I think this is it's a tricky thing, and I actually don't have super strong feelings about this, but here are the feelings that I do have, that two things are simultaneously true. One is that human beings are part of life on Earth. We're not like a distinct thing. We are animals ourselves. So animal communication includes human communication. There's a sense, there are differences in degree, but not in kind. We have common ancestors with all the animals and the plants. That's one thing that is true. Another thing that is true is that we are clearly different from other animals and plants. We're the only species that has podcasts, is a silly way of putting it, but you gotta be pretty determined not to look around you to not notice that there are some differences between human life here on Earth and the life of other animals and plants here on Earth, in part because of the ways that we think and the ways that we communicate and the ways that we manipulate our natural environment. It doesn't mean that the differences are discontinuous, that somehow something magical happened that once and for all differentiated human beings from everything else. But it does mean that certain capacities that human beings got over the course of evolutionary time gave us abilities that other animals don't have. That doesn't mean that we're special in any way. It doesn't mean that we're deserving of domain or dominion over the earth, or it doesn't have any normative implications right away. You can make normative arguments on the basis of it, but as a descriptive statement, there are differences between humans and other species, and humans and other species share a common existence here on Earth, common ancestry, made out of the same stuff, very closely related in some cases. So I don't think that any discoveries about animal and plant communication will suddenly affect our definition of consciousness. I don't know what our definition of consciousness is. I think that consciousness is kind of a vague term, and one of the things that we learn by doing neuroscience and psychology is not what is the right definition of consciousness, but what are the different aspects of human thought and being that go into making up what we call consciousness. And I think it's very, very interesting and important. And we've talked on the podcast about how other animals communicate with each other and how they think and how they reason and how it's similar and different. But I think that we should give the animals credit in the sense that when we study them, we're studying them. We're not trying to learn more about us. Sandro Stuckey says, I recently re-listened to Mindscape episode with David Wallace and noticed you promised to record an extra discussion with him as a bonus for Patreons. Did that ever happen? I like that episode a lot, so I'd love to hear the bonus. So no, it did not happen, and I think it's an exaggeration to say that I promised anything. I speculated about a possibility of doing that. And I don't know. So the reason why I am answering the question is because, I have wondered whether or not it would be worth the effort. And the answer, as soon as you say, is it worth the effort, is usually no. But effort is something in short supply right now. Are there better ways to do the model of the podcast? The current model is there's a free version that everyone gets that has ads. There is a version that far, far fewer people get with no ads for the Patreon supporters. Wondery is the place where you can get the version with ads, but it gets, sent everywhere. Whereas you have to go to Patreon and be a supporter to get the ad-free version. And so the reason why, what are the reasons why anyone would contribute to the Patreon? Well, one is just like a sense of belonging, right? Or giving appreciation to the creator of whatever it is you're supporting on Patreon. Another is that there are some benefits. In the case of Mindscape, the benefits are the ability to ask these AMA questions, and of course the ad-free versions. Is there any model where I could not have any version with ads, like have all the versions be ad-free, but nevertheless get the same income that I get from doing it because I like income and it keeps me motivated to keep doing the podcast. I would probably keep doing the podcast anyway, but I can't be sure because attention is short and I might downshift quite a bit if the income were quite a bit lower. So is there, if we didn't have ads in the regular version, I'm presuming that there would be fewer Patreon supporters, right? Because some people who support on Patreon probably do it because they don't want the ads. The number of people who ask AMA questions is also noticeably smaller than the number of people who support on Patreon. So asking AMA questions can't be the only reason. And I think that some people don't care about the ads and would be happy to support even if there were ads, but some others don't. Is there something else that I could do that would let people, that even if no version had ads, would still count as a bonus for people who are supporting on Patreon or elsewhere? Maybe there's another better way to do it with Substack or something like that. I don't know. So that's what your question sparked in me, thinking about extra bonus stuff, whether it's extra interviews or so one thing to do is maybe there's an hour or hour 15-minute regular podcast that everyone gets, and then there's an extra 10 or 15-minute more informal chit chat with the podcast guest, or a personal thing that is just me talking and only Patreon supporters get to listen to that. I don't love that idea right off the bat because it seems to require more work for me, but maybe it's something that people would prefer. I don't know. So I'm offering this opportunity, if you're out there listening, to chime in the comments or whatever, to let me know, if there is a possible way that you think, we could run things that wouldn't be a lot of extra work, but would be more valuable to you, that you would actually appreciate it more. I mean, it doesn't make any difference for me to do the podcast, even if the income were the same. If nobody were listening, I would not be doing the podcast. I do want to have an impact and give something to the people who are actually the listeners to the show. Douglas Long says, when I was much younger, I remember reading a book that discussed the two types of people in the world, competitive and cooperative. In a nutshell, being the latter and being in a position to tangle with the former, I added this to the back of my business card. There are two types of people in the world, competitive and cooperative. Competitive people push cooperative people until they become competitive. Therefore, competitive people think all people are competitive. Roughly speaking, I think that anything that starts with two types of people in the world is going to be not exactly true, an exaggeration, but, maybe a useful lens, right? And so the question is it useful to group people, even if approximately and informally, into these groups of competitive versus cooperative? I don't know. I don't know if that's actually true. I think that the number of dimensions along which it's important to measure people's essence is higher dimensional than just that one. So the competitive versus cooperative axis. So I don't know. I have nothing special to say about this other than I would worry that something like that is a bit simplistic, and it's the kind of simple rule that can seem very tempting, but you should watch out for taking it too seriously or pushing it too far. Sean Coram says, I've read in a few different popular science articles that say that while dark matter doesn't clump in the modern cosmological era, back in the era of proto-galaxies, dark matter was much more clumped up and mixed in with ordinary matter. What's going on with that? So that's just false. Just not true. The density clumpiness of dark matter is certainly higher now than it was much longer ago. Back in the cosmic microwave background days, the clumpiness was almost negligible, 1 part in 100,000. And now it is very noticeable. It's very easy to see that there's more dark matter in galaxies and clusters than in between them. So I don't know what popular science article was telling you that, but it's just not true. Joshua Hillerup says, from my understanding, there are ways to use general relativity as an effective field theory within the standard model, or with the standard model, and we haven't done any experiments that contradict what that would predict. Does that approach also make consistent predictions of what would happen with observing a tiny black hole evaporating into nothing? So, no, it doesn't make predictions about that, really. You can absolutely include general relativity as an effective field theory along with the standard model. We call it the core theory. You can even buy a t-shirt from me that has the core theory printed on it. But there are limitations. There is a domain of applicability of that theory, and black holes are not in that domain. It only makes sense to use general relativity as effective field theory in regions where gravity is pretty weak. And by construction, a black hole is not a region where gravity is weak. Now, again, as usual, there's complications, etc. There are ways to use techniques from effective field theory to do calculations with black holes, in particular calculations about the gravitational radiation from black holes. But black hole evaporation, it would be, I don't know of a way to consistently do that in the realm of effective field theory. Or let's put it this way, you would be missing the presumably important part of black hole evaporation, how the information gets out of black holes. That's kind of the whole reason why we call it a black hole information loss puzzle, because if you just do quantum field theory, you're not getting the information out from the black hole. So you have to go beyond that. So effective field theory is not up to the task. Robert Ruxandrescu says, suppose the Higgs field would turn off, go to zero value. All the quarks that comprise protons and neutrons would then have zero mass. Considering that zero mass particles travel at the speed of light, would all the protons and neutrons explode? So the short answer is no. There's a calculation you have to do. You have to ask quantitatively, would you be able to have a bound state of 3 quarks plus gluons that you would recognize as a proton or a neutron, even if the quarks were massless? Most of the energy in a proton or neutron does not come from the quark masses. The quark masses are a tiny part of the total mass of those nucleons. So roughly speaking, it wouldn't matter that much. You wouldn't change a lot by setting those masses to zero. But there is a calculation you have to do to make sure that's right. And I haven't done the calculation, so you should check me if you're skeptical about that. But there's a couple of clarifying statements that maybe might help make sense of this. For one thing, they're not particles, right? They're fields, really. Inside a proton or a neutron is a paradigmatic place where you can't ignore quantum field theory, where you really have to think about the fact that there are fields and there's quantum mechanics. It's not just little point-like particles zooming around. So to say zero mass particles move at the speed of light is actually not giving you that much insight into what happens inside a proton or neutron. Keep in mind, there are gluons inside the protons and neutrons, and they are massless. They do move at the speed of light. They would be moving at the speed of light were they to be free particles. But they're not free particles. They're confined inside these strongly interacting particles. So the right thing to do in the strong interactions in QCD is just solve the equations for low energy configurations of these particular quantum fields, okay? And you get an answer, and it's supposed to look like a baryon, like a proton or a neutron. One way of thinking about it, which I only say with some trepidation because it's a different metaphor that may or may not be helpful, is these particles are strongly interacting, so they're constantly bumping into each other and interacting with each other. So even if something moves at the speed of light, if it's stuck between two mirrors, it'll just bounce back and forth between those two mirrors, right? It doesn't mean it goes far away or explodes. It can still be confined to a small region, and yet when it's moving at the speed of light. Think of the gluons and the quarks, if they were massless, inside protons and neutrons, like that. They're moving at the speed of light, but not in a straight line. They're moving around inside. Again, that's not even actually true. They're not moving at all, but I think that's a pretty good, colorful analogy or metaphor to think about. Polheim says, when Malaysian Airlines 370 went missing, what accompanied my sadness was a sense of hope and mystery that it is still possible for something as large and well monitored as an airliner to be lost on Earth. As a devotee of the age of polar exploration, I've always wondered if something was lost from the human spirit once the poles were visited. The space race kicked off a world in which the remaining frontiers are predominantly, perhaps almost entirely, of the technological variety. That's not to say these feats are any less impressive or momentous, or to say that earlier explorers didn't exploit the technology of their day, but they strike me as fundamentally different. Do you have any thoughts on what might have been lost as a result of this transition? I don't feel that loss myself. I get it. I'm not going to undermine your personal sense of loss. I think that's a perfectly legitimate thing to think. But it's a kind of nostalgia at the end of the day. It's a game that is being played, going to the pole or circumnavigating the Earth. is much harder if you have primitive technology than if you have advanced technology. People circumnavigate the globe all the time these days, right? I'm happy that we've explored the globe. It's kind of like playing a video game, right? Where you explore the world and there are certain parts you've already explored and you don't want to do that part anymore. You want to go on to a new part. There's plenty of frontiers there that we have not yet explored, not only in outer space, but the bottom of the ocean, right? Very largely unexplored, lots of Antarctica and so forth. But, personally, if I'm talking about my own views, the explorations I care about are mostly intellectual explorations, learning things. There's many things that we don't know, and doing science and learning new things is a very real kind of exploration. There, we're nowhere close to running out of things to explore. So I don't think that the spirit of human exploration has in any sense been lost. Anonymous says, there are many animals that follow sensible survival strategies because they do certain behaviors by instinct, not because they're thinking things through and making plans. Squirrels burying nuts, etc. I see parallels to human behavior and ideas about religion and spirituality in all of this unconscious high performance in nature. We are a social species and a storytelling, meaning-making species. I can imagine it can be beneficial to our survival to tell stories about why it feels right and gets good results when we follow our instincts to cooperate. I've seen plenty of attempts to pit science and spirituality against each other, but I've never seen a scientist imply that a bird is doing anything wrong or misguided when it migrates, even though the bird is probably not acting logically, and even though the bird may very well be having an internal experience that is similar to the internal experience a human has when following a faith practice. What do you think of the idea that human religious or spiritual impulses can fit within science in the same category as a bird's impulse to migrate, as a natural instinctive behavior that some but not all people find compelling? I think that two things are being mixed up here a little bit. There's a descriptive and a prescriptive element. People can study why other people or themselves are religious, what purposes are served by being religious, what is the evolutionary basis for being religious, what are the benefits socially and individually of religious experience. Those are all things that are absolutely worth studying, just as you can study why birds migrate, right? In exactly the same way. And that's a perfectly sensible thing to do. There's no conflict between science and religion there. The conflict comes when you say, okay, I have a goal. I have an ambition to do the following thing, namely to correctly understand the universe, right? Maybe you don't have that goal. That's okay. But if you do, then science and religion, generally speaking, I know because you can always define religion in weird ways, but generally speaking, they offer two incompatible answers to the question of what the universe is and how it behaves at a fundamental level. And both answers can't be right. So if you have that goal of best understanding how the world works, science and religion are going to conflict, like turning left and turning right at a stop sign conflict. You can't do both, right? And of course, that's not the only way they can conflict. There's also questions of whether or not religion has bad implications, not just good implications, but whether it gets in the way of being a moral person or things like that. But putting all those aside, just at the level of science and religion, they're offering incompatible answers to deep questions. And that's where, to me, the important conflict comes from. And by the way, they didn't have to. Right? It could have been in some other possible world that the answers to how the universe is that were offered by religion were studied scientifically and turned out to be right. That could have been the world. It just isn't the actual world in which we live. Jared Duriagas says, as a lifelong San Antonio Spurs fan, I was spoiled by many good years in the past, but now find my team actively trying to underperform and tank for a better chance to draft a generational talent. I was curious, your feelings on tanking in sports and in general the morality of gaming systems and choosing shortcuts. I can't help but feel this question pertains to everyday life as well. Do we owe it to others sometimes to choose a harder path against our own self-interests? So I think that if you're literally a sports franchise, that is an example where it makes sense to play by whatever rules are set up. Like that's what you do in sports, right? And maybe in other wider circumstances, playing by the rules that have been set up is not the thing to do. Maybe you should rebel against the rules, etc. But if you're literally a sports franchise, you play by the rules. That's what you do. And I don't think that it's gaming the system to play by the rules to benefit the chances that your team wins a championship. That's again what you're supposed to do. If you don't like that, if you don't like that behavior, change the rules. I do think that so for those of you who are not sports fans out there, in basketball in particular, although in all sports to some extent, it's really important to have the best players, right? Of course, it's good to have the best players overall, but because in a basketball team, you only have 5 people on the court at any one time, there's an outsized influence to the best player on the team. Unlike, a football team has 11 players out there and they have completely separate teams for offense and defense. So there's lots of people who have an impact. American football, that is. Basketball, you have 5 people out there. There's some bench players, etc., but basically 5 people. So one person really matters. Basically, there's 30 teams in the NBA. And if you do not have one of the 10 best players in the league, it is almost impossible to win the championship. If you go back I did this. I was inspired by this question to actually, just check my recollections. And indeed, the last team to win the NBA championship without one of the league's best 10 players was arguably the Detroit Pistons in 2004. And before that, it was the Detroit Pistons again in the 1990s with a completely different team. So I don't know what it is with the water in Detroit that allows this wonderful sort of team basketball to be played. But other than the Pistons, if you want to win the championship going back to the 1970s, you had to have one of the best players in the league. And therefore, how do you get one of the best players in the league? Sometimes you can be lucky and be a glamour franchise like the LA Lakers and just wait for the players to come to you like LeBron James did. But if you're not one of those glamour franchises, you have to draft them when they first enter the league. And so there's an enormous premium on getting good draft choices. And who gets the best draft choices? The worst teams. There's this idea that you should help everyone get a chance by giving the best draft choices to the worst teams. But that incentivizes being the worst team. Obviously, you'd rather be the best team, but if you don't have one of those 10 best players, you're not going to be the best team, and therefore your incentive is to try to be the worst team, so you maximize your chances of getting the best player, right? The next best player. And I absolutely feel the sensibleness of the critique that says, that's terrible. You're incentivizing losing games, and everyone should be trying their best to win the games. By the way, the players and the coaches almost entirely try to win the games. When a team is tanking, when a team is trying to, as a franchise, be the worst, that's generally the front office that just trades away all their good players. So the players that they are remaining with and the coaches are doing their best. They're giving out, they're all out there, but they're just not very good. And that's a good way to get a great player. The Philadelphia 76ers, my favorite team, did that. And we have Joel Embiid, a top 2 player in the NBA right now. And so we are at least have a chance of competing for the NBA title. It works. But how do you get around that? I think that the right way to get around that, if it really bothers you, don't give the worst teams the best draft choices. That's the only thing you can do. And, people try to tweak the percentages. The NBA is constantly changing the percentage chance of getting the best pick, right? What is called the NBA lottery. But the total probability of someone getting the best pick remains constant. So all they do when they change the probabilities are move the incentives from one set of teams to another one. They don't get rid of the incentives in any realistic way. If you say the worst team gets the best pick, then you're highly incentivized to be the worst team. If you say the worst 10 teams have an equal chance, then okay, you have no incentive to be the worst team, but you have a really strong incentive to be one of the bottom 10 teams. So it can't go away. There has been suggestions for equalizing the draft equity. There's something called the Wheel, which was a proposal by Mike Zarin, who is I think a Celtics executive, which basically says every team gets a predetermined draft choice. Each year, each franchise picks in a certain sequence, and every year the sequence changes so that every 30 years you cycle through all of the different possibilities, right? And so therefore you can't benefit from being bad in any way. There's essentially zero motivation or, momentum for doing a plan like that. For various reasons. I don't think the reasons are very good, but I don't think there's anything wrong in sports or elsewhere by playing by the rules. And elsewhere outside sports where the rules are things that we make up or, someone else made up and we don't agree with, there could be more incentive to try to change the rules. But whatever the rules are, playing within them in a sports context makes sense to me. Liam Empton says, apart from their epistemological role, science and philosophy have a psychological impact in our lives, reinforcing our sense of optimism and wonderment. Do you ever see science this way in your daily life? E.g., do you listen to science podcasts outside of your field of expertise after a long, stressful day? I mean, I absolutely see those roles, science and philosophy having reinforcing our sense of optimism and wonderment. I get that. But it does not lead to me listening to science podcasts outside my field of expertise after a long, stressful day. After a long, stressful day, my long, stressful days are largely dominated by science and philosophy. So I do not de-stress by listening to science and philosophy podcasts. I would much rather read Pride and Prejudice for a fifth time or something like that, or watch the Sixers lose another nail-biter game. I think that the best way to unwind after a long, stressful day is to shift gears mentally and do something very different from whatever you do during your everyday life. So I do very strongly think that I would not be happy if I focused my intellectual efforts in a very narrow regime of science and philosophy. That's why I have a podcast. That's literally why that was my incentive for starting this more than anything else was when I was writing the big picture. I got to talk to a whole bunch of people in different fields, and that was fun. And so the podcast is a way for me to be able to talk to a whole bunch of experts in different fields. But between doing my work and making the podcast and writing and things like that, I do not have much energy left over for listening to other science podcasts. And that's not to say they're not great and you should not listen to them, and we should all reinforce our sense of optimism and wonderment. All that sounds great to me. Nalita S. says, what is the most mind-blowing physics discovery that you lived through in your opinion? What about the one before you were born? Well, I think, it depends what you mean that by lived through. I know that shouldn't be that ambiguous, but of course, I'm going to count lived through as I was a grown-up and paying attention to scientific discoveries, right? Not since I was literally a baby. And in that case, if that's the definition, then it's absolutely clear that the answer is the accelerating universe, the dark energy, the cosmological constant in 1998, which was very surprising and crucially important. It's a little bit frustrating because it's just one number. Like we measured it and we measured the number. And so what are you going to do with it? You can be inspired to try to think of an explanation for it. And I have, and people have, etc. But we haven't settled on what the right explanation is. And it's hard to do a follow-up experiment and learn more about it. If it is just the cosmological constant, which I think it probably is, then we're not going to learn anything more about it experimentally. We're just going to measure its value more and more precisely. It is literally just one number. But it was completely unexpected for me, even though I'd written about it. I'd written papers about the possibility, but I would have bet against it. And we still haven't fitted into our view of the world effectively. So that's a big deal. Before I was born, of course, carries a lot more history to it, many, many more years. I don't know if it's a single discovery, but I think quantum mechanics is the most mind-blowing physics discovery because classical mechanics was so good. It was very, very natural to think that was just the right answer, and we were just going to tweak it and find the specific forces and particles and things like that. And the idea there was a completely different paradigm was mind-boggling. And on the one hand, it's to our great credit as human beings that we were able to shift gears toward it that quickly. And on the other hand, it's to our great lack of credit that we haven't followed up, that we have not yet completely understood quantum mechanics and often ignore the attempts to understand it. Flyback says, you and other quantum physicists talk often of particles being entangled with their environment, while often referencing domains that are relative to our scale, the scientist lab, etc. Is an atom also considered an electron's environment? Do electrons within atoms necessarily become entangled with each other? Generally speaking, I'm curious about the philosophical concept of environment, its boundaries, and the effects of scale upon it. Good. I think it's good to be curious about that. It is a tricky philosophical concept, in part because it's one that makes perfect sense in a certain regime, right? In a certain limit. Like the environment, you don't need to be doing quantum mechanics to talk about an environment. Throughout the history of thermodynamics, a very common thing to contemplate is taking some physical system and embedding it in a heat bath, right? So the system itself might be at whatever temperature, but you're embedding it in an environment at a different constant temperature. And the idea of the heat bath is it's so big that the system can absorb or exchange energy with it, but the heat bath doesn't itself change its temperature or any other features. It just absorbs everything that the system does to it. That's clearly an approximation, right? And the same thing is true for our quantum mechanical environment that we talk about in decoherence. It's a convenient, higher level emergent thing. It is not a sharp, bright line that you can draw. Electrons in atoms are generally entangled with each other, but that's not an environment because we can keep track of them. The environment is literally when we lose the ability to keep track of everything that is going on. Okay, we can't keep track of all the atoms in the air around me or all the photons hitting the walls of the room or anything like that, so we group it up and call it the environment. So doing that better and better is important. I don't want to downplay the importance of really thinking through when we should think of something as the environment and when we should think of something as the system. Ashmeet Singh and I wrote a whole paper about exactly that, quantum mereology. So it's an important problem to get a handle on, but it's not one you should expect a once and for all final answer to. It's going to depend on the context, depending on your observational handles on the situation, and so forth. Francois Varchon says, in the solo episode, Why Is There Something Rather Than Nothing?, you mentioned that the answer could simply be a brute fact that requires no further explanation. Do you have any examples of other questions that can be answered with a similar brute fact explanation? If possible, one question that is more down to earth, less intimidating than the question of existence of everything. Yeah, I think there's plenty of brute facts out there. The problem with brute facts is that even though I think that they probably are out there, in other words, there are probably features of our universe that could have been different, but don't have a deeper cause or explanation for them. That's what I mean by a brute fact. And in that sense, I think there probably are plenty of brute facts, but the problem is we don't know which ones they are, right? I mean, and I do try to say, in the case of Why Is There Something Rather Than Nothing, that's an example of when we don't know if it's a brute fact or not. That question is so deep and profound, so wide in scope, that it is one of the ones where I am most likely to say, yeah, that's probably just a brute fact. It's hard to imagine something deeper that is explaining it. But I don't know, maybe there is an explanation out there. So it's perfectly legitimate to look for deeper explanations. But my point is always that just because you would like there to be a deeper explanation does not mean it's not actually just a brute fact. So we need to keep the possibility that certain things are brute facts on the table and evaluating them against the other possibilities that are out there. Siddhartha says, oh yes, remember at the beginning of in the intro, I mentioned that Siddhartha had constructed well, let me read what Siddhartha says. This is the thing that I was referring to in the intro. Since you mentioned having already answered many questions in all the AMAs you have done, I finished extracting the questions and answers for all AMAs that have a transcript into a table format for handy reference and searching, and there's a link, and I'll put the link on the website. I plan to keep this updated for new AMAs. Maybe you want to have a version of this on your website as well. Yes, I think that's a great idea. I will try to do that. So thanks to Siddhartha from me and from everyone who might want to use that. And because you've done that wonderful service, I will absolutely certainly answer your question, which is the following. The novella Anxiety is the Dizziness of Freedom by Ted Chiang describes a device that, after performing a quantum measurement to create two branches, allows people to communicate between the parallel humans in the two branches and some of the consequences of such a device in human society. One of the effects the book describes is, say, just one oxygen molecule is in a different place because of a measurement one way or the other. That can have large-scale chaotic effects on the weather and even the DNA of babies born a year later after the measurement in the two branches. Is this really likely? How likely is it that you're jumping left or right on stage, depending on a quantum measurement, leads to a different weather or due to chaos theory? I would say the answer here depends on how we construe the phrase, how likely is it? So remember, in many worlds, lots of unlikely things happen. There are worlds where super duper unlikely things happen compared to the other worlds, but they're there. They exist, right? So there's worlds where there are dramatic differences, but the likelihood that we would ever be one of the people living in those worlds is very, very small in the future. So I don't really worry about those. That's not, I think, the important question here. I think what you're asking is, how likely is it not just that somewhere out there in the wave function of the universe it exists, but how likely is it that two versions of us existing on different branches of the wave function, having only recently branched apart from each other, would find ourselves in very different worlds? And I actually don't know the answer to that question. It's certainly possible, but it's not inevitable because there is chaos, that's true, but there's also sort of dissipation and convergence. So it is absolutely possible to get completely different locations of individual atoms and molecules in a particular box of gas or something like that, just because we moved one oxygen molecule a little bit. But think about literally a box of gas, right? So if I have an exact description of all the atoms and molecules in a box of gas, I'm Laplace's demon. Classical mechanics is true. Let's imagine they're just bouncing off each other like little billiard balls. Then I can predict exactly the future. If I move one atom or introduce a different atom or something like that, those bounces will subtly start to deviate. And very soon, all of the atoms in the box will be in different positions than they would have been, okay, than in the original configuration. So in some sense, that world is now very different. All the atoms are in different positions. But guess what? With overwhelming probability, from the macroscopic level, that box still looks like a box of gas with a uniform temperature and density, etc. So there's actually not a big macroscopic difference, even though microscopically things are very, very different. That's why it is hard to answer this question. There will absolutely be microscopic differences. The question is not just, do they chaotically spread through the system, but do they macroscopically amplify? And I think that's going to just depend on a lot of physics that I don't specifically know. You can easily imagine that it's a big effect. I mean, this is literally what Schrödinger's cat was about, right? The reason why Schrödinger had to invent this Rube Goldberg apparatus was to take a small quantum superposition and amplify it to a macroscopic difference. So does that happen automatically is the question. Well, it could happen, if a certain variation in the location or firing of a neuron in someone's brain causes them to act differently to push a button or not push a button, right? And that amplifies their effects. But whether that happens automatically, I don't know how frequently it does. I'm sure it does. I don't know how often it does. Ewan McKay says, I started my PhD in theoretical biophysics this year, and I'm attending my first conference soon with a poster. So congratulations, Ewan, that's great. As someone who has presumably been to a lot of physics conferences, do you have any advice on getting the most out of it? Yeah, I think it depends a lot on your conference. The conferences are very different and what you're doing there. I think that as a young person starting a new PhD, I would mostly be in learning mode at your first big conference. So you have your poster. I would not hinge too much of your self-worth on how many people come to visit your poster or read it or anything like that, because it's just unpredictable. There's just too many things that are outside your control when it comes to things like that. Do a good job on the poster. Don't put too many words or equations on it. Everyone does, and everyone tells you not to do it, but everyone does it anyway. I will tell you not to do it. And you'll do it anyway. That's just what happens in these things. But even if no one comes, maybe you get a huge line, maybe no one comes, don't sweat that too much. I would say, like you said, you just started a PhD. There's a large landscape of things out there to learn. And, the thing about doing a PhD is it generally involves very intense, very concentrated work in an environment that has, your advisor, your fellow students, postdocs, whatever, but it's a very particular small scale environment. And there's a whole rest of the world out there. And, it's a cliche to say, if you get a postdoc, you should go somewhere far away. Or if you go to graduate school, you should go somewhere different than where you went to undergraduate. But it's really even more true than they say, because there are different attitudes towards what makes good science, how to do it, which questions are interesting, where the field is going. And you can easily get very parochial just by hanging out in one single research group or even one single university. So a conference is an opportunity, not just to learn more technical things and hear some talks, but to talk with people who are not the ones you talk to every day. Talk about theoretical biophysics. Ask them what they're working on, why they're working on it. What do they think are the most interesting things? Talk to young people, talk to senior people. Like, everyone is there to talk about biophysics, right? So this is your opportunity to, really get to know the community in a very real way. And the good news is that at your second or third conference, you will recognize people from the first conference, and you will begin to realize, here's my cohort. Here are the other people the same age as me. Here are the big names in the field and what they're doing. And you'll begin to get a sense for this complicated, hard to characterize, semi-autonomous thing that we call the community of researchers in your field. So I think that's what I would aim to do more than anything else. There's lots of things to do. You should also have some drinks in the bar and relax a little bit. Or if you don't drink, then at least relax a little bit one way or another. Don't overwork and stress yourself too much. Keith says, in theoretical neuroscience, I've recently had to become more familiar with renormalization groups and coarse graining methods when investigating potential power law and critical behavior in neural systems. I know there are similar approaches in other complex systems, such as social sciences and economics, including by former Mindscape guest Simon DeDeo. My question is, how do these statistical renormalization groups applied at these emergent levels relate or compare to the renormalization in fundamental physics made famous by Feynman and Schwinger in QED and apparently hard to do with gravity? Yeah, that's a great question. I wish that we made it more clear when we talked about renormalization. Hopefully I will try to do that in the book that I'm currently writing. The history is that these ideas started in quantum field theory because people invented quantum field theory, people like Dirac and Fermi and so forth, and they wrote equations down, Heisenberg, people like that, and they found that it was pretty easy to get an infinitely big answer, right? Feynman, of course, showed us how to convert the equations that already existed into the diagrams that we now famously know as Feynman diagrams. But one way or the other, whether they were diagrams or not, there were quantities that you were trying to compute that gave infinity when they really shouldn't. So Feynman and Schwinger, Dyson, Tominaga, and others figured out a set of mathematical techniques for basically taking a limit, right? For turning an apparently infinite quantity into a finite one. It got a bit of a bad reputation because it's kind of like making sense of infinity minus infinity, but really it was perfectly respectable all along. It was still a little bit unclear why you had to do it, but one thing that was clear was that these theories fell into two categories. Some of them have the property we call renormalizable, and some are non-renormalizable. In both cases, you can get finite answers. The difference is that in the renormalizable theories, you only have to fix a finite number of parameters in order to do that. You get an infinite set of terms that you add up to get the final answer, but that infinite set of terms only depends on some discrete finite-sized set of numbers. In the non-renormalizable theories, every one of the infinite number of terms you're adding up requires new input, requires a new parameter to fix it. So it's impossible to make any predictions because you don't know what the numbers are in the terms further down the series. And gravity falls into that latter category. It's not renormalizable in that sense. And so people had a rough feeling that it couldn't possibly be a fundamental theory, a theory that was not renormalizable, is not predictive, and therefore it can't be the once and for all final answer to nature. That changed in sort of askew ways when Ken Wilson came on the scene, and also other people, Leo Kadnov and Michael Fisher from the condensed matter side of things started thinking of renormalization in terms of energy scales and length scales. And rather than just saying I'm subtracting infinity minus infinity, Wilson and friends showed that you should think about renormalization as only keeping track of what happens down to a certain length scale or below a certain energy scale. And we don't know what happens at super duper short distances or super duper high energies. Therefore, take whatever does happen and bundle it up into some unknown quantities, which you then characterize. And so it's those unknown quantities you're characterizing that are the renormalization constants, or actually renormalization parameters that can flow as you change that energy scale you're looking at. So it was a better philosophical perspective on renormalization. Rather than just being a trick to make an infinite number seem finite, it was a physical understanding of why certain things were renormalizable, certain things were not, certain terms are big, certain terms are small, etc. It all has to do with our ignorance and knowledge at different length scales, okay? So that latter insight is what potentially is useful in complex systems, social science, economics, also engineering and chemistry and a whole bunch of other places. Look at the world scale by scale rather than point by point in space. That's the fundamental insight of renormalization theory. And it's doable is the nice thing. And in quantum field theory, it's very doable. In these other fields, maybe it works, maybe it doesn't. You got to tell me, Keith, this is your job, or Simon's job, I suppose. But maybe it does, and I think it's very possible. But I would take the actual original work by Feynman and Schrödinger, et cetera, as more a step along the path to this way of thinking about things. If what you're really asking is, do I have to read Feynman and Schrödinger or read about Feynman and Schrödinger to apply renormalization group ideas to neural systems? No, you don't, because neural systems are themselves finite. There's no infinity there because you're never tempted to go down to infinitely small length scales like you would in a quantum field theory. Lars Kruger says, as far as I know, we can't get any information about the internal structure of a black hole, but why can't we draw conclusions about it by observing the exact shape of its event horizon? Shouldn't the event horizon have valleys and mountains due to the uneven distribution of matter inside? Well, you might think that, but then people did the math, right? I say this over and over again, but the words are helpful. The words are nice. The words give us insight. It's the math that matters at the end of the day. And Roger Penrose, former Mindscape guest, and Stephen Hawking and Robert Garrosh and others in the 60s and 70s proved theorems that said that black holes do not have valleys and mountains due to the uneven distribution of matter inside. What happens to the valleys and mountains you would expect to be there? They are basically smoothed out by the black hole emitting gravitational radiation. So if you tried to make a black hole in a shape that was anything other than either perfectly spherical or an oblate sphere for a spinning black hole, it would quickly settle down to that shape by shaking off those inhomogeneities through gravitational radiation. And it happens very, very quickly. So black holes are essentially all the same. That is the no-hair theorem. It's not quite a theorem, but given certain assumptions, you can show that that's going to be the case. Dutch Cheese says, a sociology and an economics professor in a discussion remarked that they didn't understand why people were smoking and why younger people took sometimes so much risk while older people were so much more careful but having much less life ahead of them. It was all simply not rational. But I just see it as behavior that could potentially lead to more offspring. When I was younger, I also smoked because the pretty and cool people also seemed to be smoking. Do you have thoughts about evolution and rationality? I do have thoughts. In fact, as I am giving this answer here in real time, I'm realizing that later this month we have a podcast about exactly this question. So maybe I shouldn't give too much insight here. You'll get it later, rather. But what I wanted to say specifically in response to this question was, rationality is a tricky thing. When you say, oh, look at those young people, they're smoking. It's not rational. Well, what do you mean by rational? Like rationality is a procedure. okay? It's not a result, nor is it a norm. It's not like rationality is necessarily better than irrationality. But rationality only helps us achieve our goals. It doesn't tell us what our goals are. So I think that's what you're putting your finger on, and I completely agree that maybe the goal is not to maximize your future lifespan. There are other goals out there, right? Maybe you just like it. In fact, I think that almost nobody lives according to a set of rules that does nothing but maximize their future lifespans, right? You certainly wouldn't ever climb in a car if that were the case. So I think that rationality is tricky because sometimes you don't know what goals are being pursued. That's not to say that people always are rationals. People are irrational all the time, and that's very clearly true. So in a complicated case, a real-world case, like why is this teenager smoking, I would really not trust any wild guesses that I made on the basis of my own thought processes. I would want some actual careful investigation into what were the reasons that that person gave. Are they being honest with themselves? Are they being internally consistent? Is there a rational set of goals that they could appeal to? I don't know what the answer is, but we're too quick sometimes to proclaim what is rational behavior and what is not. Moshe Fader says, your discussion with Chiara Mingarelli in Mindscape 212 about using pulsars for detecting black holes got me thinking about the extreme frame dragging that a massive object spinning at 100 Hertz or more must be doing, and all the more so for any spinning black holes. So I went to read up on frame dragging, and that led to the lens-stirring precession and references to gravitomagnetic and gravitoelectric potentials, terms I hadn't encountered before. On the analogy of electromagnetism, it seemed to suggest the possibility of some sort of reciprocal generation of the forces. So are the words gravitomagnetic and gravitoelectric terminology that can be taken literally, so we can someday build gravity generators, or are they metaphorical like the colors in quantum chromodynamics? So they can be taken literally. They're literally, it's still an analogy, but it's a very close analogy. Gravity, like electromagnetism, has electric aspects and magnetic aspects. I wrote a textbook on general relativity called Space-Time and Geometry, where you can read about decomposing the gravitational field into its electrical part and its magnetic part. However, that does not mean that someday we will build gravity generators. And the reason why is because the magnetic and electric words refer to the fields, in this case, the gravitational field or the electromagnetic field, but our ability to control the fields requires sources for the fields. And the sources for the electromagnetic fields, positively or negatively charged particles, have the hugely important feature that they can cancel each other out. You can get both negative charges and positive charges. So either particle would give you an electric field, but if you put them on top of each other, you get zero field. That is an enormously powerful thing because you can take the same two things, an electron and a proton, put them very close to each other and have zero net field, and then just move them apart and suddenly you have a field, right? Or vice versa. So you can absorb fields very easily. You can create fields very easily, all of that stuff. Not to mention that electromagnetism is much stronger force than gravity, but in gravity you don't have negative charges. You only have positive masses, not negative masses. There's no case in gravity where you can take two objects which have a gravitational field, put them on top of each other and get zero gravitational field. So there's no way in a direct analogy to the generation of electrical forces that you can do the same thing with gravity. Lothian53 says, when black holes collide, they give off a huge amount of energy in the form of gravitational waves. When this happens, does it affect the information contained in the black holes? Do the gravitational waves carry the information from inside the black holes? Well, I can appeal to another one of these theorems that was proven by Stephen Hawking and friends, the area theorem of black holes. It's true that when black holes collide, they do give off gravitational waves, and yet if you take the area of the two black holes separately before they collided, the horizon area proportional to their mass, and for non-spinning black holes is proportional to their mass. It's more complicated if they're spinning, but same basic idea. And then you let the black holes collide and they give off energy and gravitational waves, but they haven't shrunk overall. there was also energy, in the gravitational pull between the black holes. And the area of the black hole, the single black hole that you made, is always greater than or equal to the combined areas of the two black holes you started with. You cannot decrease the total surface area of black holes by combining them. So if you think that the information is proportional to the event horizon area, it does not go down when you take two black holes and squeeze them together. Schleier says, I've come to believe that I am a 99% non-sentient zombie. My only evidence of consciousness occurs when I'm thinking about consciousness, which is not often. All I am is this brief instance of introspection occurring in this brain at this place and time. I will cease to exist in a moment when my mind's attention wanders, and it's back to zombie status. Do you think you are conscious when you are not thinking about being conscious? Is this even a meaningful question? Yeah, I think, as I said just earlier, that consciousness is a complicated thing and there's different aspects to it. You seem to be choosing an especially demanding notion of consciousness, that you literally have to be conscious of your consciousness to be conscious at all. I think that's not necessarily true. I think that's, at least, let's put it this way, not what most people have in mind when they think about consciousness. When you smell something and it smells like cinnamon and you go, that's cinnamon, to most people, that is a conscious experience. You go, oh yes, that smelled like cinnamon. You don't need to be thinking, oh yes, I am conscious of smelling cinnamon, right? That's not a necessary part of the whole thing. So that's a different level. Maybe you want to call them two different things, and one is consciousness and one is not, but that's just a matter of the definition. More importantly, I think that one's attention to conscious introspective experiences comes and goes. Yes, your mind's attention wanders, but in the conventional way of thinking about consciousness, the fact that you are conscious, a conscious creature, does not actually come and go. I mean, you're not conscious in the usual sense when you're asleep, but you're still a conscious creature who is just not activating their consciousness at that point in time. I think that's the way most people would talk about it. James Swift says, what dish or meal that you prepare and cook yourselves at home do you feel gives you the best return on investment? Investment meaning effort, time, cost, or whatever you think is the most interesting definition of investment and return. I think it's an easy question for me. I make pan pizza in a cast iron skillet that is to die for. I gotta say, it is so good, but you'll never taste it because I'm going to eat the whole pan. It's a pretty big, it's a 12-inch skillet. It's a lot of pizza, and it's so good that I'm going to eat the whole thing. It's not very involved. I'm not an expert pizza maker in any sense. You can go to Whole Foods and buy pizza dough and buy pizza sauce and mozzarella cheese, and then, I fancy it up with pepperoni and onions and oregano and things like that, garlic, but not that much effort, huge payoff. So that's answering your question. It might not be the best thing I make, but in terms of effort and payoff, it's the biggest ratio there. But I will say I am trying to cook more. I've always been someone who can cook a little bit, a follower of recipes, but it's never been a major part of my activities. I'm also very happy to go out or just do TV dinners or make some spaghetti or whatever. I'm trying to be better at actually cooking real food. We have a big house now, and we can have people over and cook for them. And, a part of our lives where we have the jobs we want, Jennifer and I, and we can have people over and we don't need to worry about moving somewhere else. We're here for the long term. I got to learn some dishes to cook. Had some people over very recently, and I made this Greek lemon meatball soup that was really quite good. A huge amount of work because you have to make the meatballs. But it was worth it because it was yummy, and you just can't buy that pre-made. So I'm trying to be better at that, trying to cook more. It's both fun and creative and better for you than just heating something up in the microwave. Crather Luca says, in a recent podcast, you brought up the argument from evolution against moral realism/objectivism. Is this something you believe in? To me, this is just an argument that we need to do philosophy to create moral progress rather than relying on our instincts. Just as we have to do science to create better theories of the physical world rather than relying on our instincts. I don't think that the argument from evolution against moral realism is a very strong argument. It's certainly not a knockdown argument, but it's suggestive. It's one of the ways in which you can sort of raise questions about moral realism. So for those who don't remember or know the argument, the idea is basically, look, if there was no moral realism, if there were no objective moral truths, what would happen in the world? And, there would be people would exist, right? And they would come up with rules, as we talked recently with Michael Tomasello and others. People very naturally, being social creatures, would invent rules, would invent standards by themselves that correspond to ideas of good and bad. In other words, we would invent morality, whether or not it was out there. And we would invent it for reasons of evolutionary pressure because, we're trying to get along, we're trying to survive, trying to pass down our genomes, etc. And the argument, such as it is basically if you thought there were objective moral truths out there, there's no relationship between those objective moral truths and the ones that we invent through evolutionary pressures, right? There's a total different set of reasons why we invent our, ways of living socially than some out there in the sky moral truths. So why should you think that these objective moral truths just so happen to line up with conventional human morality? As you can see, it is not a knockdown argument because maybe they do just happen to line up. But I do think it's sort of a winking acknowledgement of some of the unrealistic aspects, I should say, of moral realism. It's much easier for me to believe that we invented morality for reasons of social interaction and evolution and things like that, and then attributed objective reality to it, even though we had just invented it, than it is for me to believe that there really are absolute moral principles out there that we have discovered through thinking really hard, and we just keep happening to discover ones that line up with what we wanted to be true anyway. That doesn't seem very realistic to me. James Mahoney asks a priority question. We've gotten this far without a priority question. Remember, the idea of a priority question is that everyone who asks AMA questions gets one chance in their lives. We're assuming that no one is going to be living for thousands of years here, but one chance in your life to ask a question that I will absolutely try to answer because I can't answer all the questions. So if you have one that you really, really want answered, just label it a priority question. I will give it my best shot. There is no guarantee that I will do a good job answering the question or that you will be satisfied with the answers. Sorry about that, but I will give it a shot. So James's question is, I sent you a copy of my book, The Logic of Social Science, Princeton University Press, at your philosophy department address. I think you will like it. Did you receive it? If so, would you be able to glance through the beginning parts and let me know what you think? So yes, I did receive it. It is very relevant to things that at some point in my life I want to think about, The Logic of Social Science. But no, I've not read it yet. I just don't have time to read it. There's a lot of things I need to do right now. I'm probably busier and have more obligations right now this academic year than I ever have in my life, to be perfectly honest. So there's many things that I've been blowing off and not doing, and reading books that come in the mail has been one of them. Hopefully I will get to some things later, but as of yet, not yet. Jeremy Dittman says, your fascinating discussion with Joanna Hoffman on designing future cities and the strategy of employing a storytelling narrative space made me think about your previous Mindscape guest, T. Nguyen, and our human tendency to construct simple narratives that are false and ultimately unhelpful for understanding what's going on. Historically, the development of the scientific method seems like an antidote to this over-reliance on simple narratives to explain the world around us. Do you think that there will be an effective scientific method for attacking complex systems still waiting to be developed? What credence do you assign to the storytelling narrative approach to problem solving when it comes to complex human systems? So I do think that we are and will continue to develop an effective scientific method for attacking complex systems. I think that the very phrase complex systems doesn't necessarily map on to any particular part of the world in an easy way. There's different kinds of complex systems, and they may ultimately require different kinds of analysis. There do seem to be, happily, some commonalities in the complex systems that we know and love, and maybe we can leverage those commonalities to improve our effective scientific understanding. But there's also just, rules of thumb. That, there's ideas that come along that we do realize are helpful in understanding complex systems that fall short of being really scientific principles. One such is that, there can often be, this actually has a name. I forget the name of the principle, but, there's aspects of complex systems that are a certain way, and no one can remember why they're a certain way. But they're really important, it turns out. If you stop them, if you get rid of them, everything falls apart. There's a conservatism that complex systems naturally inspire because tiny changes can lead to large effects, right? So these are not scientific principles, they're rules of thumb. And that is why I do think that this storytelling narrative approach to problem solving can be relevant to exactly this kind of situation, these complex human systems. There's, coming up with good ideas is something that we've not yet been able to turn into an algorithm. Human beings can come up with good ideas, but we're not ever completely sure how we do it or even how to duplicate it next time. And I'm all in favor of using all sorts of different techniques to inspire us to come up with good ideas. And there's something about storytelling or fiction writing or imagining future scenarios that nudges us to think in slightly different ways, nudges us to take certain things seriously that you might not have thought of, or to think of aspects that you might have overlooked. It is far from perfect. There's plenty of examples of stories and narratives that leave important things out, right? But because complex systems are so complex, they're hard to boil down to hard and fast rules. Thinking in these more imaginative ways, I think, can be absolutely helpful in the foreseeable future anyway. Heikki Lokkanen says, if consciousness is the ability to think of an internal self, and theory of mind is more or less the same but for other people, which do you think developed first? Our ability to attribute thoughts, desires, and intentions to others or to ourselves? I love this question. I have no idea what the answer is. I think it's a great question. I'm kind of surprised I never thought of it before, or no one else has mentioned it to me, or maybe they have and I've just not paid attention to it. That's very, very possible. But yeah, did we first start conceptualizing other people as agents, if you want to put it that way, as Michael Tomasello talks about, or do we consider ourselves as agents? I forget even if Tomasello gave an answer to that question, even though he wrote a whole book about the evolution of agency. So I'm sure he would have an informed answer to this question, and I don't. I think I would guess that we did it to other people first in some sense, right? I mean, we develop models of the world, and that we need to do that to get through life, even, way before we become human beings, evolutionarily speaking. There are models of the world, like if you do this, then that will happen. Animals definitely have such models. And so, of course, you're going to include others in your model of the world, right? I mean, my cats absolutely have a thought that if they act in certain ways, I will respond in certain ways. Do they have self-consciousness where they think of their own intentions and desires? Probably not. So therefore, on the basis of that conjecture, I think that we probably developed, we probably started thinking about others first in these ways. But maybe I'm skipping over the importance of not just having a model of other people, but that model including the idea of agency. So I really don't know. I think it's a good question. Aaron Munger says, is there an easy way to think about the more counterintuitive cases of growing entropy, examples such as oil and water becoming cleanly separated into layers, or a big cloud of atoms that will clump into the planets of a solar system? I have a hard time seeing how there are more ways to arrange the parts of the higher entropy state while keeping the macro state the same. There are ways, but maybe they're not easy. So I talk about both of these examples in From Eternity to Here, if you want to read about it. In both cases, once you dig into the details, the oil and water separating or the gas clumping into a planet or a star, the entropy is going up in a very standard way. It's moving toward a configuration where there are more ways that the system can be arranged. What is secretly going on, though, is that the total arrangements that are possibly accessible by the system include aspects that you don't see. So you think that something counterentropic is going on. In the case of oil and water, what's going on is that the oil molecules are, let me get this right, either hydrophilic or hydrophobic. They're hydrophobic. They don't like water. So if they were, let me try to get it right. It's been a while since I wrote that book, and I'm not a chemist by any stretch. If you have an oil, maybe they're hydrophilic. Yeah, maybe they're hydrophilic. If you have an oil molecule and a water molecule, they tend to lock together, right? They tend to like arrange into a certain configuration. And so it's only the combined system of the two molecules that can move around and have degrees of freedom. Whereas if they're separated, they can both move around independently. So the entropy is actually higher. The number of accessible states is actually higher when they're separated. So they like to just completely separate and have a boundary between them. In the case of the gas and dust collapsing to a black hole, to a star or a planet, that only happens because the system can shoot out some escaping atoms or dust grains or whatever. So the momentum in the escaping bits is very high, and the total amount of phase space available in high momentum escaping things is big. So when you take the momentum as well as the position into account, it's a higher entropy state when gravity is important for things to be lumpy than for things to be smooth. So in both cases, they're moving towards macroscopic configurations where there are more possible configurations, but you don't see the relevant parts of the configurations with your eyes, so you're getting tricked. Red Antonov says, is there a past guest you would like to write a paper with? What would it be about? This is a good question that I'm not going to give a very good answer to. I have written papers with a couple of past guests. Adam Rees, my current Johns Hopkins colleague and one of the discoverers of dark energy. I collaborated with him and with the group on one of their early papers, the High Z supernova team. And of course, Scott Aronson and I wrote a paper together. I think that's it. Among the, I've come close with a couple of other guests, but I'm thinking about this. I don't think I've collaborated. I feel very bad. Sorry, guests that I have had on the show that I'm not remembering the papers we wrote together. But probably there's a bunch of people who I would like to write a paper with, but there's just a finitude of energy and effort available here. I have to prioritize what I'm doing. There's a lot of ideas that pop up during the podcast that I just don't have time to chase down. And, it takes work to write a paper. Writing a paper is not just having an idea. That's the easy, fun part. Then it's like months of effort to really think through that idea, read other papers that other people have written relevant to that idea, come up with some examples or some calculations you can do, to make it into a substantial of enough investigation that it's worthy of being a publishable paper. So, who knows? Like I said, between moving to Hopkins and writing books and things like that, my research has slowed down recently. I'm very, very much looking forward to getting back on my feet there, and I have a whole bunch of things I want to get done. Maybe some of them will be in collaboration with former guests. Steve Wood says, priority question. I'm genuinely curious about how you see your audience and what you honestly expect them to understand. I've been wrestling with this question since way back in episode 36 with David Albert. I fully accept that I may not be informed enough in many of the physics categories you discuss, but how many of us do you think are? Is the kind of conversation and the kind of abstraction going on in that Albert podcast meant to tease us, baffle us, motivate us to reboot our entire education, or just impress us? What do you really expect to achieve with these discussions beyond anything like social status building? I don't ask that to be rude. I just wonder who benefits. The intention is absolutely to help you understand things. Different people might achieve different levels of understanding listening to different podcasts. Different guests might be better at using words that everyone can understand, and others might not. That's the nature of the game. The nature of doing a podcast where I'm talking to other people is that I do not have complete control over what those other people say. I try to do my best to bring on guests who I think are very interesting and have something important to say that can be made understandable. I personally did not find the David Albert podcast to be that difficult to understand, even compared to some other podcasts. But I get that depending on what you're used to reading and thinking about, it might have seemed impenetrable because of different parts of the vocabulary or whatever. That's perfectly fine. But it is. It certainly has nothing to do with social status building. If anyone is under the impression that they're going to build up a lot of social status by listening to Mindscape, then keep listening, but I would change your motivation for doing so. Gregory Kusnik says, Nikki Haley thinks we should have competency tests for older politicians. My feeling is that if we're going to have such tests, they should apply to everyone, not just the old. What do you think? Yeah, I don't think we should have competency tests for older politicians or for anyone at all. I don't know. I mostly can't imagine what kind of test would do good, right? Like, I get the motivation. You want your politicians to be competent. I think that it's beyond a doubt that some politicians get to be a certain age, begin to lose their competency, and yet stay in office for various reasons, right? But I think that the solution to that, and I think that's bad, but I think the solution to that is not competency tests. That just seems like a cheap gimmick to me. You have to be more serious about it. Ask yourself the question, why is it possible for someone who might not be that competent to nevertheless win an election, right? And that has to do with all sorts of things, largely involving the benefits of incumbency, whether it's fundraising or name recognition or what have you. I think that incumbents have too much of an advantage overall. And I think that that's a bigger problem than people getting old and less competent. So that's what I would aim at, not cheap gimmicks like competency tests. Okay, we've reached the end of the AMA. There's one more question to go. This is kind of a fun one from Nick Gall. I'm fascinated. Well, I think it's fun. I mean, you might not think it's fun. Nick Gall says, I'm fascinated by the issue of how Hilbert space is carved up into classical macroscopic objects, aka systems or entities, and environments, but I'm confused by the lack of any unified terminology. There seem to be so many different names for this issue in different contexts. Decompositional equivalence, defining wave function branches, physics from scratch, preferred basis, preferred decomposition, quantum factorization, quantum mereology, quantum reality, set selection, static state, what's a system, and then there are names attached to all of these, including my own quantum mereology with Ashmeet Singh. So the question is, the lack of unified terminology makes finding papers on the issue very difficult. Why is the terminology so fragmented, and when do you think it will become more unified? So I get that this can be frustrating. This is part of what, is what makes research hard, is that there might be something out there in somebody else's paper that is really relevant to what you're doing, and yet you don't know about it and you can't find it even though you looked. And the best is when you end up writing your paper anyway, and then someone sends you a annoyed, irate email saying, "Why didn't you write my paper? Clearly you hate me." And you have to say, no, I didn't know your paper existed. It has nothing to do with my personal feelings toward you or disregard for your work. So this is a problem. But there's a reason why it's a problem. There's two reasons, actually. Or there's a reason why the situation is what it is. One is that even though the various terms that you have cited here all fall into the general bucket of carving up quantum states and their evolution in useful ways, many of them have slightly different actual physics questions that they are pointing at. The preferred basis problem is guess what? A problem about a basis in a vector space, whereas a preferred factorization or decomposition is a question about subsystems, not about basis states. And those are two different things, even though they're all in the bucket of trying to carve the world up in ways that are useful to us as big macroscopic people. So that's part of it, that these really aren't exactly the same. But the other part is, this is an area that has not received that much attention. I mean, you're listing, a dozen papers, but that's a drop in the bucket compared to, the total number of papers written about quantum mechanics one way or the other. There's not a coherent group of people who are dedicated to the idea of understanding how to carve up the wave function into classical bits. I wish there were. I am trying to, build up exactly an enthusiasm for this kind of research, but in a situation where a set of questions is not yet popular, people are thinking about it, but it really hasn't taken over, it really hasn't grabbed the imagination of a large swath of people, and we don't know the answers to the questions, and we're kind of feeling out what the answers are, it's very natural that people are going to invent their own terminology for what they consider to be slightly different things. The hope is that it all kind of settles out. What is the word I'm looking for here? Shakes out. That eventually we get together and talk to each other back and forth and agree on what the right words are. You know, some of these phrases, quantum reality or what's a system, these are not very helpful. These are not very specific labels for the things that we're thinking about. And, you know, preferred basis or pointer basis is a good one, but it's a different question here. So I think we'll get there. You know, patience, you know, as time goes on, and you cite this website by Jess Riedel, who has done a very good job at bringing together some of these different things. And that's how the academic project works, is that people write papers, they try their best to cite each other. Sometimes they fail. Other people collate different papers and point them out and try to bring them to other people's attention. I mean, you might remember, or not remember, but you might know the story that when Hugh Everett wrote his thesis about many worlds, no one paid any attention to it. That was in the 1950s, and he left academia. So the fact that he left academia meant that there was no person out there popularizing his idea, okay? And turns out that's a super important aspect of the research process. It turns out that Bryce DeWitt was the editor of the journal in which he published his paper, so he knew about it. And over a decade later, in 1970, DeWitt wrote a paper in Physics Today, popularizing, and he labeled it The Many Worlds Interpretation of Quantum Mechanics. And then people started paying attention to it. You know, as we talked about many times on the podcast with Zeynep Tufekci and other people, attention is the coin of the realm. There's a million things going on in the world. What are you paying attention to? Who are you listening to? We talked about this at the very, very beginning with the black hole paper that's supposed to be dark energy. I certainly think that I could, if I spent a day or two, read through this paper, really understand all the equations, and come to an informed judgment about whether or not it's on the right track. But there's a million papers. I can't do that for all the papers, right? I can't even read the abstracts of all the papers that come out every morning. There's just too many of them. So you need some filters. You need some filters to decide what to pay attention to. And for this particular set of questions about dividing up the wave function of a big system, it's never been pressing because people thought they knew what the subdivisions were. When I have two electrons in front of me, I have two electrons, and I combine them to make a two-electron system. This inverse problem of starting with a combined system and asking how to divide it up isn't one that has been very pressing, so people don't pay attention to it. I think as we push forward into understanding the foundations of quantum mechanics and quantum gravity, people will pay more attention to it, and in the process, we'll pick some words and stick with them. We will pick some terminology that makes sense. But the exciting go-go early days are never going to be that crisp and clean. That is a motto to keep in mind for the foundations of quantum mechanics as well as for everything else in life. So with that, thanks very much for listening to the AMA. Talk to you next week/month. Keep going. Bye-bye.